If you just do it, it'll turn out okay. Hey everyone, we're back for Talking Time with Caffeine. I just got done watching Dapper Dino watch a Kent video, very ranty and stuff, and now I need some education in my brain. You don't know Tony, but today we have a new guest today.
Is this your first time, Dan?
This is my first time talking on this show. So, hello, thank you for having me. I'm Dan. My channel is Creation Myths, and I'm an evolutionary biologist. So, and my specific training is in the evolution of viruses. So, this is a really interesting time to be somebody who worked on viruses in grad school. It's never good when this many people are interested in what I did in grad school. It's not a good sign.
Yeah. Oh, it's more interested in my subject in tech school. I worked on printing presses in school.
I didn't do any studying on viruses at all. I've never done any of that, but I do a lot of research, as you guys probably know, and this is something I'm fascinated by. So I'm glad you guys had me on.
Awesome.
Tony, I'm getting a little bit of roboting. Is that on my end or yours?
I hear it too.
Okay.
But anyways.
Okay, then it's on my end. I'll fix it. See what I can do.
Sorry.
So let's start with, I guess we start with the basics. What are viruses?
What are viruses? That is a fun question. So I always define viruses as a subcellular, intracellular parasite. So something that is smaller than cells, it doesn't have all the components of cells, but it gets into cells and parasitizes them. It steals their stuff to make more of itself. And then the other kind of side of what a virus is it has to transmit to a new host cell via some stage where you've got a protein coat with the DNA or the RNA on the inside. So those are kind of the two components of being a virus. You got to be less than a cell, get into a cell, take it over, and then you have to transmit to a new cell via what's called an encapsulated stage. If you do those things, you're a virus.
Yeah, I think some people are confused with viral infections and bacterial infections.
Yeah. So a bacterial infection is an actual cell. It has different components. And bacteria they have what's called a plasma membrane. They have a cell wall, and then because they're cells, they kind of can live on their own. They don't need some other entity to like do a bunch of the legwork to make more of them. So what cells that make us sick do, like think about like bacteria that cause like strep throat or something, get strep bacteria in your throat, it'll live on your tissue and damage your tissue, as you know, just that's how it makes its living, whether it's in your throat or, you know, an ear infection will be in your middle ear, it could be in your lungs, it could be anywhere in your body. And the important thing with the bacterial infection is that, at least for now, they are susceptible to antibiotics, which are a extremely diverse group of chemicals that are actually naturally occurring. They're just part of the natural arms race that's out in the environment. And we've taken these chemicals and used them medically to kill the bacteria that are infecting us. Now, viruses, you can't treat with antibiotics. They're not susceptible to all those different things. So you need different approaches when you're dealing with a virus. So you get different antiviral medications, or a kind of a better approach is to use vaccines to prevent the infections in the first place.
Yeah, I think about vaccines and viruses. I heard some people they're starting to treat, instead of antibacterials, they're treating bacteria with viruses.
Yes, they are. It's one of the coolest things, and it's something that's going to be like a thing. I don't know when, but we're running out. You've probably heard that we're running out of antibiotics, that the rate of antibiotic discovery is very low. We're not finding new antibiotics as rapidly as we used to.
And the bacteria are becoming immune to them too.
And the bacteria are becoming more immune faster. So they're developing resistance faster and faster, to the point where what used to be the threshold of resistance where we wouldn't use an antibiotic clinically anymore because the dose would be too high and you'd have too many side effects. We've actually lifted that threshold to ensure that we can keep using certain types of antibiotics in certain settings. So the alternative to antibiotics is something called phage therapy, because there are viruses called bacteriophages that infect bacteria. These are phage means eat. So bacteriophages, the word literally means bacteria eater, and they're viruses that infect and kill bacteria. So what you do with this is you take a culture of whatever bacteria it is that's causing an infection. You grow it up in the lab. You allow viruses in the lab to infect that bacteria. So the viruses get really good at infecting that particular type of bacteria. And then you give the person with the infection the viruses, which then kill the bacteria that's causing the problem. It's a really cool approach. It's not approved in the United States yet. I believe, I'm sure someone can give me the specifics on this. As of a couple of years ago, I think there was a phage therapy trial going on. I don't know what the status of that is right now. But if you have the money, you can go to Warsaw or Tbilisi, which is in Georgia, Asia, Georgia, not United States, Georgia, because those are the locations of the former Soviet phage therapy labs. And during the Cold War, the Soviet Union had a robust program of phage therapy. So we actually have, this is a technology that we already have, and it's already used clinically, just not in the United States, but it will be at some point in the near future. We're not talking decades and decades from now. We're talking maybe 1 or 2 decades from now.
And unlike the antibacterial, if the bacteria become resistant to the virus can just adapt to the bacteria again.
Bingo! The viruses also evolve. So you get this arms race between the bacteria and the virus. So the bacteria will develop resistance, but the viruses are also an evolving population. So they're going to be able to counter that resistance pretty readily. That's what we see in the lab. And oh, go ahead.
As I said, and from what I've been hearing about this virus, I was afraid of. It's already starting to adapt. So I was hoping maybe it still will be. I was hoping it would be like a one shot and done thing, but maybe like the flu and we had to take multiple shots.
That may end up being the case. We don't know. What's nice so far is with this, so people have probably heard of this new variant of the coronavirus that I think it maybe first appeared in the UK, and it's now in a couple of different places. There isn't a whole lot of information about it yet, but what we've seen so far is that the vaccines that we have are working just fine, even with the new variant. So that's good. That's lucky. What may end up happening is it may end up in a situation where it's similar to the flu, where you get a yearly kind of thing because it's a slightly different strain that circulates. With like the group of viruses that we're talking about are the coronaviruses, and this is the 7th. So this is SARS coronavirus 2. This is the 7th coronavirus that infects humans. And so 4 of them just circulate and cause the common cold. 2 of them were pandemics. So you had the SARS pandemic back in 2003, 2004, and then MERS, which I think first emerged in 2012 and kind of on and off until 2014. And then it pops back up periodically, but it's not a huge problem. And then so there were 4 kind of common cold ones, no serious illness, 2 pandemic ones that were very dangerous. You're talking like 10 to 20% mortality rates with those. And then this one, which is kind of in between. In terms of transmission and being dangerous. What may end up happening, because those normal common cold ones, you get one, and then you're resistant to it for like 2 to 3 years, 1 to 3 years. So it may be the case that with this one, it's kind of a rolling kind of thing where you get a vaccination for it or you get infected by it, and then you're good for 2 or 3 years, and then you need another vaccination or you're once again susceptible. We don't actually know. Because the other 2 pandemic ones, the SARS-1 and MERS, we don't have good data on them because those pandemics ended.
Yeah,
so we don't know what the long-term situation is.
I don't remember those 2 that well because I don't remember it wasn't that big on the news or anything. But this one really shut everything down.
They infected far fewer people. SARS-1 only infected each one, I think, only infected a few thousand people worldwide. It was basically they infected far fewer people, but the case mortality rate or the case fatality rate was somewhere in the neighborhood of 10 or 20%. For I forget which one was which, but they were both extremely dangerous. To put that in perspective, if something has a case fatality rate of 1%, that's incredibly dangerous. So 10% is almost unheard of. That's extremely dangerous virus. Yeah, and there were a lot of precautions. I remember there were a couple of cases in Canada that had everyone kind of freaked out a little bit for the original SARS, but it kind of got tamped down pretty quickly, and it petered out. It didn't become like this worldwide thing that we kind of lost control of, like what happened here.
Yeah, see, vaccines. I heard with chickenpox vaccine now, I missed it by a few years because I didn't like the early.
Me too.
I like in the early 80s, so I having a little bit later after that, so I just missed the vaccine.
I remember. It's funny, my siblings and I actually straddled that. So I got chickenpox when I was in first grade. My whole first grade class got it. There were out of 27 people in that class, I think like 14 people got it. It just went through everybody. But my two younger siblings got vaccinated against it, and they never got chickenpox. So we're just a couple years apart. So we straddled that line there. So now this vaccine is really cool because it's this new type of vaccine. It's this mRNA vaccine, which is super exciting. And this is the kind of thing that I've been telling my classes for years. I talk about the immune system, and I talk about vaccines, and I've been saying, okay, we have this type of vaccine, and there's also this fourth one that we don't have any yet. But when we do, it's going to work really well, and hopefully we'll be able to use these soon. And then now, for the first time, not for a great reason, but now for the first time, I'll be able to say, and here's this new kind, and this is the vaccine that you all just got, and that'll be interesting to change up how we do that discussion.
We have a question for you.
Oh, let's see. Question: why are extremely lethal viruses far less common than less deadly viruses? Great question, because you would think like a virus's job, right? It gets into a cell. It kind of bull in a china shop. It takes over. It breaks the cell. It makes a bunch of copies. And it gets out of the cell and infects more stuff. You'd think the better it is at that, the more dangerous it would be. So the better viruses, the ones that are more successful, would be more dangerous. But you hit a point of diminishing returns because you're a parasite. And if you're a parasite and you kill your host really fast, that doesn't help, right?
Yeah,
that actually hurts you.
You gotta find new hosts.
You got to find a new host real fast. Now, there are some viruses that make that work. Like, think about Ebola, right? I don't know how much either of you or anybody in the audience has read about Ebola virus, but Ebola is really gross. It basically separates all the layers of cells in your body from each other, and then you just bleed like everywhere. And it spreads through fluids like that. So the worse your symptoms get with Ebola, the more it spreads. But with many viruses, that isn't the case. And kind of an example of this, it's overly simplistic, but think about like a common cold versus the flu. Now, a common cold spreads really easily because like you get the sniffles, but like you can handle it. You don't have to take a day off from work. So you're out and about, you're blowing your nose, you're washing your hands, hopefully, but probably not perfectly every time you blow your nose, right? You're gonna, touch doorknobs, you're gonna shake hands, maybe you're going to be in the same room as people. So that cold virus is going to spread around. But if you have the flu, like, I don't know if anyone's had the flu recently, but having the flu is awful. Everything hurts. You don't want to get out of bed for like a week. You're just not encountering that many people. Now the flu, because the symptoms are far worse, it actually inhibits its ability to find additional hosts. So that's kind of an idea of that trade-off. That trade-off does not always hold, but it does in a lot of cases. And that's what's going to, so you have kind of this trade-off between like how dangerous are you versus how efficiently can you spread through a population. That's sometimes the case.
Now, I might be wrong about this, history, I might have heard this wrong, but if and the history might have been wrong too, obviously, but the first vaccine that I know about was the cowpox, smallpox vaccine.
Yeah. It was Edward Jenner in like the 1800s, And it's a great story. Can I tell the story? Is that okay if I nerd out and tell the story? It's so cool. So this was, and that's actually where vaccinia comes from. It comes from vaccinia is the name of the organism for cowpox. I think it's for cowpox, and the word vaccine comes from that, because the cowpox virus was the first vaccine. And what happened was, it was during the Napoleonic Wars. Somebody realized that for whatever reason, cavalry soldiers didn't get sick when there was a smallpox epidemic in the army during the Napoleonic Wars, and technically it's the Wars of the French Revolution, and so whatever, but late 17, early 1800s. And what happened was they eventually realized, and the other group of people that didn't get sick from smallpox was milkmaids. What people realized was that they were actually infected by cowpox, which could infect horses and spread from horses. And they would, if you got cowpox, that would confer resistance to smallpox. They were similar enough that the immunity from a cowpox infection made you less likely to get severely ill from a smallpox infection. So they started inoculating people with cowpox on purpose. They'd give you cowpox on purpose, and that means you wouldn't get sick from smallpox. And that is, I'm not exaggerating to say that single discovery, probably more than anything except sanitation, has saved more lives than any other invention, probably with the exception of sanitation. It's just that is one of the most incredible, important discoveries, not just of the last 200 years, it was a little over 200 years ago, but just ever in the history of humanity, in terms of improving the general safety of being a human.
And is that pretty much how vaccines work even today? You give yourself a weaker version of the virus, so your body can get used to. Your body knows what it can get used to attacking it, and then sees the real thing. It's like, oh, I know that thing. Kick its butt.
I know that thing exactly. So some vaccines still work that way. So there's a bunch of different types of vaccines. You've got your inactivated vaccines, which is where you take the virus or the bacteria, because you can vaccinate against viruses, bacteria. You could vaccinate against big parasites, eukaryotic parasites. So there's now a vaccine against malaria. There's a malaria vaccine now, which is a eukaryotic parasite. So the idea with these with the attenuated vaccines is where you take the thing that makes you sick, you grow it in a different environment. And like for polio, for example, the famous for most of the 20th century and into the 21st, the polio vaccine was an attenuated vaccine. It was the actual polio virus. It was just weakened because it was grown on monkey cells. And when it mutated and got better at growing in monkey cells, it got worse at infecting humans. So you could get infected with this weakened polio virus, and before the polio virus mutated again inside you and got dangerous, you had built up the immunity to it. So that's one approach. Another approach is called an inactivated vaccine. You take the pathogen and you kill it with chemicals or heat or whatever. You just boil the thing. Okay, you've got your intact virus or your intact cells, but it's dead. And you inject those, and your immune system still sees them and still freaks out a little bit and recognizes them. So like the flu vaccine every year that you get injected is an inactivated vaccine. There's whole flu virus in there, but they're dead. And then the third type, the second newest type, is called a subunit vaccine, where instead of the whole virus, it's just the piece that your body recognizes, whether the protein that sticks out on the surface, maybe that your immune system sees and makes antibodies to. You just inject a whole bunch of that. And then when you see the real thing, you go, aha, I've seen this protein before. You don't care what the protein's attached to. You just see the one thing, and you can attack that. And then the newest one, of course, are these RNA vaccines, where you bring in the RNA, which is the nucleic acid that your cells use to make proteins, and you bring in the RNA to make those surface proteins for the virus. So you make your own, and then you learn what to target. And the advantages of that last one are that you can get a much higher dose of the protein, because each little piece of mRNA is going to lead to a lot more proteins than you could fit into a single shot. So these RNA vaccines, awesome. This is potentially groundbreaking. Now, if we're lucky, we can now vaccinate against things that we previously couldn't, because we couldn't generate a vaccine that caused a robust enough response. with the RNA vaccines, we might be able to do that now. So this may open up a lot of doors into new preventative measures, which is really exciting.
Yeah, and like each virus can with not vaccine, they attack different types of cells.
Usually, yeah, it depends on the virus, but not always. So, like, influenza is really picky, right? Influenza attacks just your lungs. It doesn't attack anything else. It doesn't replicate, like, in your nervous system or your intestines. It just does your lungs. But the funny thing is, in different species, influenza viruses do different things. So, like, everyone's probably heard of, like, avian flu, and we're always worried if, like, an avian flu is going to jump into humans. Well, avian flu doesn't affect bird lungs. It affects their intestines. But when those viruses mutate just a little bit and they jump into humans, now it's a respiratory virus.
Yeah.
But they tend to be specific. Now, that's different for other viruses. Ebola doesn't seem to care that much. That just goes wherever it wants and it infects whatever it wants.
Like the AIDS HIV virus, they attack the white blood cells that attack other viruses, which makes them dangerous.
Devious. Yeah, right. Because it makes if you're affected by that, then it makes you susceptible to lots of secondary infections, because the virus basically does a the way I always think about it, it's that scene at the end. I don't know, this is an old reference. I'm sorry, everybody. But in the original Men in Black, where Will Smith it was Tommy Lee Jones gets eaten, right? And then he blows up the alien from the inside. Sorry, spoiler alert. That's basically what the HIV virus does. It basically says, it doesn't try to hide from the white blood cells. It says, hey, I'm over here. And then the white blood cells engulf it. And that's how it gets in. And then it takes over once it's inside. Devious.
And then you could die from the common cold even, because your cells aren't there to attack the other ones.
Yeah. Yeah, the dangerous thing there are infections that aren't dangerous to non-immunocompromised bodies. So, I mean, you're talking, a yeast infection, Candida albicans, or a type of virus called cytomegalovirus, which everyone's infected with cytomegaloviruses. By some estimates, our immune system spends like 10% of its energy dealing with cytomegaloviruses, but they're easy to deal with. They don't make you sick most of the time. But if you're immunocompromised, they can cause all sorts of problems. There's types of pneumonia that you can only get if you're immunocompromised generally. That was actually how the AIDS pandemic was found. It was a rare type of pneumonia that was documented in a couple of different places. And it was literally one person put two and two together and wrote it up in the CDC. It's called the MMWR, the Morbidity and Mortality Weekly Report. And it was in like 1981, this one person, she was just like, you know what, this is weird with this pneumonia over there, and we've never seen this before. And that's considered the beginning of the AIDS pandemic, because it was the first time anyone had said, like, something weird is happening here.
Oh, yeah. But vaccines and anti-vaxxers, are they a new thing, or they've been around for a long time? They're now internet.
Forever. There are political cartoons from Jenner with anti-vax propaganda. They've been around as long as vaccines have been around, as long as the concept of vaccination has been around. You can find it's called, I just Googled it, it's called the cowpox. It's called the cowpox. And it's a old-timey political cartoon from like 1800 or so, and it's Jenner injecting people with cowpox, and then those people are subsequently turning into cows. So, yeah.
Yeah.
So anti-vax propaganda has existed as literally as long as the concept of vaccination has existed. The internet's not helping, but it's certainly not new.
Yeah. My favorite one is the vaccine gives you autism. I'm like, okay, I'll take. If it's true, I'll take the autism.
I mean, that goes back to literally there's one study. It was 1998, I want to say. It was Andrew Wakefield. And this guy, this British guy, British doctor at the time, although he not anymore, because he can't do what he did. So what he did is he was coming up with, so he was targeting specifically the trivalent, the MMR vaccine, the measles, mumps, rubella. And not by coincidence, he was developing a single version of one of them. I forget which one, measles, I think, but don't quote me on that. And basically a competing treatment or competing vaccine kind of course to the MMR course. And he literally paid like the participants, he like paid parents to have their kids produce like blood samples for his work. It's not even enough to say that it was fraudulent. Like he literally just made stuff up. It's insane how like blatantly just lying he was. He literally just made stuff up for his famous paper that was subsequently retracted, and he lost his medical license and yada yada yada, but the damage was done. You can't unring that bell once you publish such a study. I mean, my goodness, everything about that paper is just wrong. And it goes back to Wakefield basically having a financial interest in the MMR shot having a problem so that his competing product would be used instead. And to say it was fraud is an understatement. But
apparently, even so, from our hearing, even then, he still believed in vaccines because he wanted his vaccine.
Still believed in vaccines. He just wanted you to use his vaccine, not this dangerous one over here. Yeah. Mm-hmm.
But then other people took it off in a whole new direction.
Now we're just gonna go. We're gonna take that and turn it up to 11. Yep, that's it.
Yeah. Like I said,
and here we are. And
yeah, I have a friend whose mom actually has polio because he was born before the polio vaccines. So my friend is really for vaccines because he's seen her mom suffer through it.
Yeah. Oh yeah. It's a lot. I think a lot of it is generational because like people my age, your age, we're pretty close in age. We didn't grow up with people getting measles. We didn't grow up with people getting mumps or rubella. Like that stuff was, polio. That stuff was largely gone. So we didn't have friends in elementary school that got polio and died. We didn't have any, but we don't know anybody as kids. I never didn't know anyone as kids that got measles and got really sick. I didn't know anyone that got measles as kids, right? Because everybody was vaccinated. So we get this kind of false sense of security, and you get anti-vax people that are going, why do we need to do this anyway? Look at how few cases of measles there have been in the last 20 years or whatever. It's like, well, the reason for that is because everybody is vaccinated. If you're standing in a rainstorm, but you have an umbrella, you don't go, oh, I'm perfectly dry. I guess I can put the umbrella away. Like the vaccines are what is making it safe. The fact that it's safe doesn't mean we can stop vaccinating. It just, it makes my head hurt.
Yeah,
it makes my head hurt.
I had a few seasons ago. I had a friend who literally can't get vaccines because her body can't handle it. So she realized other people doing like herd immunity or whatever.
Exactly. So you have to make sure that enough people are vaccinated so that the pathogen can't spread. So you can cover the people that are immunocompromised, that have an allergic reaction, that are on chemo, like all these different groups of people that can't get vaccinated. It's on everybody else to vaccinate so we keep them safe. Yep.
Yeah. Oh, so how come, I guess it probably is evolution, but like some viruses like the measles, mumps, polio and stuff, chickenpox are one and done, but other ones like the flu are seasonal?
Yeah, it's a great question. So some viruses, it has to do with what the vaccine targets. And certain viral proteins are going to evolve really fast, and other ones are going to evolve much more slowly. So like the influenza, for example, the targets for that, because of the structure of the virus, the targets for that vaccine are the ones on the outside that interact with our cells, not just the cells they infect, but our immune system cells that are like, aha, this thing. So the virus, we actually by the virus circulating, by us vaccinating, we're imposing a selective pressure on that virus for the rarer variants. So if you have a variant that's really common one year and you do a really good job immunizing everybody against that variant, well, that variant is going to be really rare the next year, right? And a rare variant is going to become more common in its place. So the vaccine that you had last year, that immunity works. You'll still make antibodies to that virus. but it's a slightly different strain of that virus that's going to be circulating. So your antibodies from last year aren't going to work. So you need a new flu shot. And that's kind of the challenge with influenza. And we talk every year about, like, is it going to match? Is it going to work? Some years it doesn't work. And it's because by like March, April, May every year, you have to look at what the trends are for the different strains in the influenza population and make a projection about what they're going to look like in September and October to have that vaccine ready by September for the next flu season. So you have a really quick turnaround, and you're basically taking a couple of years worth of evolutionary history and then trying to project forward for the next 6 to 8 months, which is an extremely challenging problem.
But the older ones, like the measles and stuff, they don't evolve that fast, or didn't evolve.
They evolve, yeah. The target that we use for them, and I don't know what the targets are for many of these, all of them, but the targets that we use are stable. For whatever reason, some viruses, they don't change things very much. Maybe it has to do with if there's a mutation to that protein, it doesn't work. If it's part of the coat or something, maybe any mutations that would allow it to evade your immune system based on the vaccine, any mutations might inhibit it structurally, so the virus wouldn't work as well. I don't know, and I'd expect it to be different for as many groups of viruses as there are. But it's just the case that some viruses evolve slow enough that we can vaccinate once during childhood, and you're good for decades. And then what we're finding is, in some cases, it seems like decades later, not 5 years later, but maybe 20, 30, 40, 50 years later, maybe you need a booster to just make sure you're good.
Is that like with the was it with the shingle shot in your 50s, whatever?
Yeah, that's a weird one, because that's actually the same. That's such a weird one. That virus is weird because that is the same virus as causes chickenpox. It's the same virus, but what it does is you get chickenpox, and that's like the acute infection, and it infects your skin, and you get angry, red, itchy spots all over your body, and then it goes away. Your immune system defeats it, and it's done, and that's not going to happen again. But those viruses that hang out in the cell bodies of your neurons, specifically neurons in your spine, where if you could picture this, you got your spinal cord, right? And you've got neurons that have the cell bodies in your spinal cord, but then the axons, they radiate to either side. So they go out, to your ribs, your arms. Some of these axons can be like several feet long. And it's one cell. It's just this long, spindly, basically a wire where it sends signals. And the viruses will go into this kind of dormant state. The intact viruses, and they'll just kind of go into stealth mode, and they'll hang out inside the neurons for decades. And then later on, they'll just be like, I'm here now. And they'll ride that axon out to the surface of your body. And that's why you get like weird little patches on the periphery for shingles. It's whatever neuron happened to be infected. It's where does it end? That's where you get the rash on the surface. It's such a weird virus. I don't know of any other viruses that do that exact thing. But then basically you can, once you've gotten either chickenpox or chickenpox immunization, you can then have a secondary immunization to prevent that other thing from happening. It's so weird. It's so weird.
Really question for you.
Question?
Yeah.
Was there a question in the chat? Oh.
Yeah, right there.
Oh, yeah, 100%. So what I would say is it's not that they evolve like to be vaccine resistant, because they're not like trying, but what'll happen is vaccines can actually impose a selective pressure. So if you have a population of viruses, right, and 90% of them are susceptible to the vaccine, meaning if that population gets into somebody who's been vaccinated, 90% of those viruses, say, are now going to be targeted by the immune system. Well, which viruses are going to be the ones that survive and replicate and spread to a new host? It's going to be the small fraction of the population that was not susceptible. So the vaccines, it's similar to like antibiotics, where by using it, you're imposing a selective pressure and potentially promoting the variants of the virus that are not susceptible.
And the ones that survive, that people, when they tell you to take all your medicine, if the bacteria or the whatever survives, they can mutate
exactly,
and not to be able to like, oh, we survived this,
right? So
anything.
Yeah, so with viruses, you can't, a vaccine is an on-off switch, right? Either you get the vaccine and you get the response or not. With bacteria, it's a little bit different because it's the You could feel better 3 days into a 5-day course of antibiotics. The problem is you haven't killed all those bacteria, and the ones that are still alive are the ones that survived 3 days of antibiotics. You want to kill those. You want to make sure those are dead, because when they come back, if they've already survived 3 days worth of antibiotics, you're not going to feel better after 3 days on the next time if they come back. So that's why you got to do. That's why you got to do the whole thing.
So, let's see.
Oh, I see a lot of good questions in the chat.
Okay.
These are good. These are fun questions.
So you could click one and answer it.
Yeah, here. How about I just see Scott Duke saying, if viruses aren't life, how close do they come to being life? What is the scientifically defensible definition for life? I love this question because so biologists love to do this thing where we put stuff in boxes, right? We say, this is a species. Everything goes in that box. This is a different species. Everything goes in this box. These things are alive. These things are not alive. That's dumb. We shouldn't do that. There's a continuum. And so you can look at cells, right? Cellular life. Generally, if you're alive, like by the high school definition of living, you have to have cells. But there are cells that are really tiny. They're parasitic. They're maybe missing parts of their genome that like do important things. So they have to live like attached to a bigger cell.
Yeah, it was good that. I was wondering about this. I might be wrong. Like if maybe I don't know how it really works, but if RNA and viruses were the first life forms, and then some of them split off to become the first cells with DNA, and the other ones became the viruses with the RNA.
I have a weird theory about this, and I have no support for this idea other than it makes sense based on what we see in the world right now. But what we see is overlap, right? So in all the activity of like what cells do in terms of their size, their biochemical complexity, all the stuff you see, a big range. And then viruses typically do less than all those things, but they overlap the cells. So if you got your cells, I'm trying to keep this framed here. So you get your cells like this. Your viruses are maybe like this. Generally smaller, less complex, but there's overlap in terms of the size of the genome and the number of genes. There's overlap between the biggest, most complex viruses and the smallest, simplest cells. And then you have other entities, things like plasmids and viroids, transposable elements that are smaller and simpler and less complex than viruses, but there's still overlap in there. So what I think happened early is you had a bunch of just reactions going on, and different parts of those reactions got kind of contained within compartments. One type of compartment became cells. Different types of compartments became the different types of viruses. And one thing we know about viruses is that unlike cells, they don't share a common ancestor. Like all cellular life, from humans all the way down to the smallest, simplest bacteria, we all share a common cellular ancestor. But that's not the case for viruses. All these different groups of viruses have independent origins. So there are multiple independent origins for viruses by multiple different methods. There's one group of viruses that are really big. It's possible that they're like degenerate cells, basically parasitic cells that started transmitting via like a viral-like state, right? There's another group of viruses. It's a group that infects plants that it was a plasmid. It was a completely different thing. There's this little circular piece of DNA that infects bacteria, and it stole a capsid gene from a different group of viruses. So you could take this group and divide its genome in half, basically. Half the genome matches up with this one group of plasmids. The other half matches up with this completely different group of viruses. And it's this weird chimeric genome, completely new group of viruses. Like, they're super weird, and there's no one origin. So trying to draw a line between viruses and cells in terms of living, non-living, I don't think it's a useful approach because there's so much overlap and interaction between all the different components. Plot twist. It's the Andromeda strain. It's actually the Andromeda strain, everybody. They came from outer space. That's it. It's over. I actually see one question here that's kind of related to that. Is it possible for a virus to get infected by another virus? Yeah. There's a group of viruses called virophages that basically they can infect a host cell, but when they infect on their own, they can't replicate. But there's a bigger virus that infects that host cell and takes over. And then when the virophage infects, it takes over the bigger virus's machinery and converts the big virus. Instead of making more of the big virus, it just makes a lot of the little virus instead. It's called a virophage, which is actually, some people will consider that evidence that those giant viruses started off as cells. And then the virophages infected the cells and stuck with them as they kind of shrunk down into a group of large viruses.
Yeah, on the same, we'll back up a little bit. On the same, I remember something that happened earlier last year. On the same face as anti-vaxxers, the anti-maskers that attacked this year, movement attacked. My favorite thing was like people said they couldn't breathe through the mask. They couldn't breathe through the mask. And they said, "Well, if you can breathe through the mask," people would say, "If you can breathe through the mask, then you can get the virus through the mask." And I'm like no. It's like viruses may be small, but you know what's even smaller than viruses? Molecules, like carbon dioxide molecules.
Yeah. The whole I can't believe that was on it. Like, I am astonished that was a real argument that people were making, but people were actually saying that the masks, if they're able to block the viruses, then they will also block oxygen. And for anyone who doesn't know, oxygen that we breathe is 2 oxygen atoms stuck together. It's O2. And a virus is like millions of times bigger than that.
You won't mix up viruses, atoms and molecules, like everything else.
A lot of them. And the coronaviruses aren't even particularly small as far as viruses go. They're not huge, but they're also not tiny. They're pretty complex. I mean, they're enveloped viruses, so outside of their protein coat, they have a membrane. They're pretty large. I won't say they're large, but they're not tiny in terms of viruses. There are smaller viruses that are much harder to filter out of the air than what we're dealing with right now. There's a reason medical masks are designed the way they are. Like, there's a reason they're designed specifically that way, because you use them in a medical setting to prevent things like viruses from transmitting.
Yeah,
what they're designed to do.
My other argument was that I can't wear a mask for 10, 20 minutes to go to a store to get something. And lots of doctors have to wear a mask for 6-8 hours in surgery.
Yeah, 6, 8, 12 hours. I mean, no. Wear a mask. Wear a mask, everybody. Even as the vaccines are rolling out, wear a mask just to be safe. Because, we don't know, there are no documented cases of anyone that has gotten vaccinated subsequently transmitting the virus. There are only a handful of cases of people getting vaccinated and then actually getting the virus. Of those, there have been no documented cases of transmission from someone that was vaccinated. That doesn't mean it can't happen. So until we get the all clear, even if you're vaccinated, when you go to the supermarket, you're going out in public, whatever, still wear the mask.
Yeah, that's an American thing, or is that in the other countries of the world too?
I mean, I think a lot of it is probably the American, individualist thing. I think a lot of it is the American anti-science, the reflexive anti-science thing. I also think just in general with the masks, there is a healthy dose of, I don't know if racism is the right word, but kind of, I don't know if xenophobia is too strong, but basically looking at it as primarily a thing that people in East Asian countries would do, and not particularly effective, kind of quaint, but they do it and it makes them feel better, and that's fine. And it turns out, rest of the world, that the public health experts in those countries actually do know what they're talking about. And they actually are effective at preventing the transmission of not just SARS coronavirus 2, but also things like influenza and common colds. Because one thing you'll see this year is that we're actually, so far, fingers crossed, having a mild flu season, because all of this behavior like masking is also limiting the spread of influenza. And that's really useful. And even once we're done with this pandemic, that's something we should keep. We should, it should just be a general thing that if you're feeling, if you got a cold or you think you maybe have the flu, and you have to be around people, wear a mask. Just common decency, wear a mask.
Yeah. So I remember it's going to end when it gets warmer. It's just going to end when it gets hot, or it's going to get in the fall when the flu.
I'm old enough to remember when there were 15 cases, and in a few days it was going to go to 0. I'm old enough to remember that. So the thing that surprised me about this whole thing, actually, I don't know how political you get typically, but I have
a few. I usually don't, but like a few weeks ago, me and Tony and Eric were talking about the election fallout and how that happened. So if it's that big of an event, then I might talk about it.
I mean, the thing is, like, I had conversations, like, my relatives, I remember like it was yesterday, last February, my relatives would be like, what's going on with this virus? Should we be worried? And my response was like, look, we deal with this kind of thing pretty regularly. You know, we had the SARS pandemic in 2003. There was the H1N1 in 2009. There was MERS in 2012. There was a 2014 Ebola outbreak. Like, there is a pandemic playbook. There is a pandemic playbook.
Yeah, but back then we had people that actually knew how to deal with it. And
I figured, silly me, that we were just going to follow the playbook. Because, like, there is a way to deal with pandemics. And, like, it's not a secret. Like, look at places like New Zealand, Vietnam, South Korea. Like, there's a playbook. Oh, there's a pandemic. Okay, let's do all these steps that we know is how to solve that. Like, there is a playbook that you follow, and if you follow all the steps well, you don't have a bad pandemic. And we just, not only did we not follow the playbook, not only did we not read the playbook, we set the playbook on fire and threw it away. Like, we were just like, we're going to do the opposite of what you should do in this situation. And that is what surprised me the most of any of this, that we just completely said, you know what? We know how to deal with this, and we're just going to do the opposite of that. And like, I am still shocked that we just collectively made that decision.
Yeah, I heard Clorox kills viruses. Let's get some Clorox.
Man, it's I will never not be shocked by that, because literally, like, and not even like, okay, you don't want to have it. Nobody wants to have a pandemic on their watch, but like, like, there's an alternate history where presidents could run for any number of terms, where Barack Obama just cruised to his 4th election on the strength of his pandemic response, because he shut that thing down and we had minimal disrupt. Like, there is an alternate universe where that happened.
Yeah, that's probably why we didn't hear of the 2014 pandemic, whatever, 2008 pandemic wasn't that big of a deal. I mean, probably because we took care of it.
We had a playbook. We had a lot, like the 2009, I was in grad school during the 2009 swine flu pandemic. It was fascinating because I got to watch it in real time as like, and I like, my stuff was about viral evolution. And some of my colleagues, like, they actually tracked disease outbreaks. They didn't track human disease outbreaks. They tracked like disease, plant pathogens. So things like cassava, mosaic viruses, and tomato yellow leaf curl, stuff like that. And we're watching this in real time as they're tracking the 2009 strain and the H1N1, and it was just you had massive surveying. Anytime there was a potential flu case, it was, what is it, where are they, isolate, contact trace. Like, it was on the ball. And like, it's hard. It takes effort and experts and money to do. And we just decided not to do it. And here we are. And I see, like Australia did well, but a bunch of businesses went out of business. I would put money on it that it's more than 7% here. Because like, having to shut down and not have customers that's a big problem. But it's a worse problem. Having a pandemic where 500,000 people die is a worse problem for business. Like, man.
My favorite response was, like this virus is only killing 1% of the population. I'm like, that's still 1% of the population. That's still a lot of people.
That's great. Let's get 100 random people and see who volunteers. Like, come on.
Be like 1% of 7 billion is like what? Still 700, like 70,000 people, 700,000 people. That's still a lot of people dying.
It's a lot. It's a
If you
lot.
want-
Now, for what it's worth, what we're finding out, I think is probably the case, is that the case fatality rate for this virus is lower than we originally thought because in the spring, we just didn't have the testing capacity. So if you look at the graphs, right, they look like this, right? They got a bump in the spring, and then the summer's not bad, and then there's that summer bump, and now we're in the big winter bump, right? But
Yeah.
that spring bump from like March into and through April, that's probably about 1/10 of what it should be.
Yeah.
So, we
Yeah.
just missed so many of the cases.
But Dan, if we stop testing people, we'll stop getting so many results.
That's the magic, right? That's how it works.
Uh,
Man.
yeah, and what was that? I don't hear that much anymore, maybe a little bit, but what was that thing that when they first started about the medical bump thing to keep it under the loop or something under the
Oh yeah,
curve?
it's called flatten the curve, right? So the point was if you could picture it like this, you have some kind of capacity of like ICU beds, ventilators, whatever you need for treatment, you have a capacity for that. And if you have more people sick that need that stuff at any given time, if you exceed that capacity, then that excess is much more likely to die because they're not getting the treatment they need. So the original idea with the flatten the curve thing was if you look at those early projections, you're going to blow right past your capacity, and a lot of people will die unnecessarily. So what you want to do is take that really tall, steep curve and make it wider and flatter. So even if the same number of people get sick, even if the area under the curve stays the same, at no point do you cross that threshold of your capacity of your medical system. So even if everyone is getting sick, the same number of people ultimately, it's happening over a longer period of time. So you don't exceed your capacity and fewer people die. The other side of that is we learn how to treat it better. We're really good at treating coronavirus right now. We're light years ahead of where we were in March, right? We're so much better at treating it now. So by drawing those cases into the future, a case that we may have treated incorrectly in, say, April, right, that maybe would have died, we'll treat it correctly in August and will survive. Right, so that's the other side of it. By drawing it into the future, we're going to be better at this in the future than we are in the present. So the more you can push it, the better.
Yeah, it's funny. In February, we pretty much rebuilt our whole lobby at McDonald's. Like we were closed for a month. The lobby was rebuilt. We opened up for a week, and then shutdown happened.
So back down.
We spent all that money. I'm like, we can spend that money rebuilding the kitchen, have our equipment's falling apart. We had to get the lobby fixed up for no one to use.
And eventually it'll get there. And like right now, I think I forget if it was today or yesterday. It was probably, we don't have the numbers from today, so it had to have been yesterday. But I read that there were 1.6 million vaccination shots administered. Like, keep that number going. We got another vaccine coming on the scene soon. Two actually, AstraZeneca and J&J are going to be there soon. I forget which one, but one of them is only one shot instead of two. Plus, it was just reported, I think today or yesterday, that we're going to have enough doses to have 300 million people vaccinated by the end of the summer, which that's it. Like, the problem with that is you're going to have kids who are too young because we haven't completed the trials. The way the trials are working is they're stepping downwards in age. So you get, at first it's 18 and above, then it opens up to 16 and 14. I don't know where they are now.
Yeah, like the first, either the older people and then maybe the people that are like that have pre-existing conditions, maybe.
Right. But then the other problem, getting 300 million people vaccinated, is what we're calling vaccine hesitancy, which is people don't want to get vaccinated, which seems not rational to me.
Because the anti-vaxxers got in their brain, or they are anti-vaxxers.
I mean, it's not even like the militant anti-vaxxers. It's just like the occasionally good faith, poorly reported stuff that you see. Part of the problem is it's a new type of vaccine. People are worried about, like, well, what does this RNA vaccine do? People are worried that it like changes your DNA. But the thing to remember, RNA, and in particular it's called mRNA, is the specific molecule, it's super unstable. Once it gets into the tricky part with these vaccines is getting them into your cells. You have to have like a little lipid particle to do that. Once it gets into your cells, that mRNA lasts about 5 minutes. And in those 5 minutes, you make a ton of those viral proteins that you want your immune system to recognize. And then at that point, it's basically a subunit vaccine, just with a higher dose. And so it's just a little part of the virus that's now inside you that you've made. And your immune system sees it and goes, that's not me. I need to be ready to kill that thing. So now your immune system can really ramp up, and it's a much larger dose. Because think about like a protein that your immune system recognizes, you inject a certain number of those proteins, and that's the dose. But if you inject the same number of mRNAs, you make a bunch of the proteins from each mRNA, so you get a much higher dose, a stronger response. Everybody's good. And yeah, it's the mark of the beast. Yeah, it's the that's the technology for the mRNA vaccines is just fantastic. And it's, like I said earlier, because you get a more robust response, you feel kind of like poop after your second shot. I was actually in the Pfizer trial, and they just unblinded us. So I actually got the real vaccine in the Pfizer trial back in October, November. And I knew I'd gotten the real thing because the day after my second shot, starting like 12 hours after my second shot, I had a mild fever, chills, body aches. Like, it felt like I had the flu a little bit. It lasted about 24 hours, but by the next day by the next evening afterwards, I was fine. It was one day of unpleasant, and I was happy about that because that meant, one, I got the real thing, and two, it was working. And that was really cool.
That reminds me, I've heard this a few times about anti-vaxxers that they're saying we should have a placebo vaccine for people for trials and stuff.
So we do. This was a full placebo-controlled trial. The placebo was a saline injection.
Okay.
Now, what they'll sometimes do, because what they want to see is that known vaccine versus new vaccine, what they'll do is, as the placebo, they'll give you a different vaccine, kind of a well-established vaccine. I forget which one they use, but sometimes they use it's instead of a true placebo, which is just a saline injection, it's a vaccine placebo, where it's a different, well-studied, nothing out of the ordinary vaccine, and then they compare I just got vaccinated with this known thing versus I just got vaccinated with this unknown thing. Right? That's the other way of doing it. All of the trials for this new vaccine were true placebo-controlled trials, with the exception of one, and I forget which one, but one of them did use the kind of vaccine placebo, but the other like 4 or 5 used true saline placebos. I don't know where they get that from. Like, no, it's placebo-controlled. Like,
what is the point of what do placebos do? What's the point of that?
Nothing. That's the point. It's the point that it has no physiological effect. So you can say if 5% of the experimental group report a certain set of side effects, but 1% of the placebo group report that same set of side effects, then that tells you that of that 5%, not all of them are due to the vaccine. Because there's something else in there, the injection, the volume of liquid, something else about that thing was causing some of those side effects.
Or it could be
or
it could have been nothing at all. It could have been something totally random,
Yeah.
the vaccine at all. If both parties are getting the same thing, and like,
Yeah, and this is important for other treatments, because you get a treatment, right? You get a new drug to treat whatever condition. Well, if you get a placebo, if with that new drug, say you get 10% of people see an improvement in whatever condition, but then you get the placebo and 8% of people see improvement in that condition, well, is that drug really doing anything? Not really. For whatever reason, 8% of people apparently are going to improve one way or the other. So, like, is that drug that improves in 10%, like, worth it? Who knows? It's that's the importance of your placebo control, is that you need to see if the effect that you're observing is actually from the thing that you expect it to be from, or if it's just happenstance, a side effect, whatever, of the process that you're doing, or maybe it just would have happened anyway.
all right. So, can anybody in chat have questions for Dan here?
Questions, please. This is super fun. talk about
Anybody
vaccines,
on
viruses, and stuff all
anybody
night.
here on YouTube, Twitch, or Facebook? Come on down. You're your next contestant. like this.
I have YouTube open, but I don't have the other ones.
Well, you can check this on this comments on the side.
I had was a president who worked at science. I had not my congressman, but a nearby congressman was a physicist, and I think he had bumper stickers that said "My congressman is a rocket scientist" at one point, which I like that a lot.
What's your favorite TV show?
What's your favorite TV show? Man, I don't watch a lot of TV. I really don't watch a lot of TV. I will say, if anyone has not watched The Wire is required.
Yeah,
watching.
I haven't watched. It's been years since I've actually watched TV anymore. Since the most stuff's on Hulu or Netflix.
I will say there's an ongoing season of BattleBots, and what can I tell you? I'm in. I am in for BattleBots.
I would still, yeah. But I still have to say my favorite show. Still, Boy Meets World from the 90s. Still my favorite.
Classic. In terms of stuff that's on now, I'm behind, but I want to catch up on The Expanse. And I still haven't finished. I still have a season of Peaky Blinders to do. So those two I gotta get caught up on. Oh, how did HIV spread so quickly? Yeah, because you would think being not exclusively, but primarily sexually transmitted, that HIV would be tough to spread. That's true. The thing with HIV that's so tough is that it has a really long incubation period, depending on the strain of HIV, 6 months to 10 years before you get sick from it. So if you are infected,
you don't know you have. You don't know.
You get an acute illness, and then it kind of goes away, but then it builds back up, and then you can have anywhere from a few months to almost a decade, where you don't really have symptoms, but you're actually able to spread the virus. So what if you look back at the history of the HIV pandemic? You see it really explode in the early 80s across 3 or 4 continents simultaneously, like boom, boom, boom. Where did all this come from? And one of the initial things that was confusing is because everyone thought it had to be different viruses, because you can't have an epidemic of the same virus simultaneously on 3 continents. It has to start somewhere and it has to move. But with HIV, it crossed into humans probably around 1930, and then it spread at very low levels under the radar for decades. And it didn't start really spreading a lot until the 60s and really in the 70s. But then all those infections that happened in the 70s, you don't start seeing them until the early 80s. And that's when it exploded.
And it's not just a sexual, probably sexual disease. Yeah, it wasn't just a sexual disease either. Like the famous kid from the 80s or 90s, that Ryan guy didn't have by having sex.
Exactly. Yep. Blood transfusions. Yep. So there were blood transfusions. There was a famous case of where a dentist infected his patients because it was a cut on his fingers in the mouth. That was a very famous case. It was actually the first use of DNA in a courtroom, was determining whether the dentist did actually infect the patients, which is an interesting case study. It's an interesting. If anybody is interested in that, there are 2 books I cannot recommend enough. One is called The Coming Plague by Laurie Garrett, which it's not just about HIV, it's about emerging diseases. So there's chapters on HIV is like a novella in there. It's like a 200-page chapter. But then there's Ebola, there's bubonic plague. I learned from that book that every decade or so, there's a bubonic plague outbreak in like the southwestern United States. Just like, no big deal. It's just something that happens every 10 years or so. There's a chapter on influenza, smallpox, all kinds of stuff. Great book that's called The Coming Plague by Laurie Garrett. And then specifically for HIV, it's And the Band Played On by Randy Schultz. This book is incredible. It's much more of a kind of it's not just about the science. It is about the medical side and the science and the epidemiology, but it's also about the social and political aspect of it. And for that reason, it is absolutely infuriating. And the band played on, but it is a just fascinating read about the kind of the first decade or so history of the AIDS pandemic. It's an absolutely incredible read. Cannot recommend it enough. Oh, favorite virus? I really like the big weird viruses like Mimi virus and the aptly named Pandora virus, which, true story, it's the biggest known virus, and we isolated it from melting Siberian permafrost. And then we said, I wonder if this thing still works, and brought it in a lab and tested it against a bunch of cells, and it turns out it still works, even though it had been frozen for tens of thousands of years. But there's also a place in my heart for the virus that I worked on in grad school. It's a teeny little weird single-stranded DNA virus called Phi-X174. And I dig that virus.
Oh, that reminds me that people are saying that this virus was created in a laboratory somewhere.
Oh, you mean the SARS coronavirus too?
Yeah.
No, because we have the genomes. We can look at the strains and we can see where it came from. And it very clearly did not come from the lab in China. It came from bats. You can do a phylogeny of this virus, and it falls out in a clade where it's just bat coronavirus, bat coronavirus, bat coronavirus, bat coronavirus, SARS coronavirus 2, bat coronavirus, bat coronavirus, like it's from bats. We figured that one out. I have not read that book, The Chimp in the River, but I'm going to read that book. Hot spring. I'm not familiar with that hypothesis. I don't know. Yeah, I don't know. Oh, it's recent. That's a real recent one. Yeah, I don't know that one, but I'll have to look into it now. Thank you.
Yeah. So that's you read this book? You said that you haven't read this book.
I am not familiar with that book, but I just wrote it down. I'm going to read it because yes, please. Yeah, it's fascinating. There's a really good Radiolab, actually. It's an old Radiolab episode. It's probably like 8 or 7 years old at this point. But yeah, it's a really good episode on the origin of HIV. Very cool stuff. Favorite abiogenesis hypothesis. I'm weird. I don't know how familiar people are with this, but with abiogenesis, with how life emerged.
I did a whole series on this about how that one is the only hypothesis. Not technically, they're not theories yet. They're still the hypothesis.
Yeah, there's a bunch of competing hypotheses with varying levels of support. And right now, so for a long time, the controversy was protein world versus RNA world. And now what we're seeing is it's probably some combination of those two. And you can get like what are called ribozymes, which are RNA enzymes, and then simple polypeptides interacting with each other that can do some pretty complex things. But then the other side of that is a question of kind of metabolism first versus structures first. So do you get like the chemical reactions and then they end up in cells? Or do you have like protocell structures and then the metabolism develops inside them? And I started on the protocell side of things, and I've been convinced that metabolism first is more likely correct. That you've got just big kind of metacycles of chemical reactions, and then they get contained within like lipid structures later.
Yeah, that would be even though that would be probably very boring, not exciting, but it's probably more interesting to actually have two real competing views on a debate instead of just the usual evolution creationist debate. Because
I would watch the heck out of a 2-hour debate between a protocell first person and a metabolism first person. I don't know who those people would be, but I would love to just watch them just hash it out for 2 hours. I would love that.
To both actually have an actual. Either one could be right viewpoint instead of just
right. There's legit evidence for both. It's not that the thing with abiogenesis is it's not that we don't have a plausible model. It's that we have more than one and we don't know which one is best. And that's a really cool situation to be in.
With the RNA first thing, I always wondered if maybe like but like since RNA and DNA both have three similar what that word's called, but three letters in their thing are the same, but only one letter is different. I always wondered maybe if DNA became when RNA, the one letter in RNA mutated to form the DNA letter.
Okay, I got to tell this story because this is my favorite thing. Like, literally, this is you accidentally, you had no idea, you could never have known this, but you just hit on my, like, legitimately my favorite thing in biology, which is, so the letters, the bases for DNA, A, T, C, G. For RNA, it's A, U, C, G. It's uracil instead of thymine. Why is that? That's weird. Why is that? Now, everybody agrees, there's no real controversy that RNA was before DNA. We'll agree on that. The reason we switched from uracil to thymine is because of cytosine, because cytosine sucks. Cytosine is way less stable than the other bases, and when cytosine mutates, it mutates in a very specific way, really fast. It does this thing called deamination, and when it does that, it turns into uracil. So if you have a genome that has cytosine and uracil in it, and you come upon a uracil, you don't know if it should be there or if it should be cytosine. Now, the solution to that problem, this is a great example of evolution being a tinkerer rather than an engineer. Because an engineer would look at that problem and go, okay, this is dumb. Let's get rid of cytosine and find something that works better, that's more stable so it doesn't constantly mutate into this other thing that we use. But that's not the solution we found. The solution we found was get rid of thymine, or get rid of uracil and replace it with thymine. Because then, anytime you see uracil in your genome, you can go, aha, that should be cytosine. And to this day, every cellular form of life on Earth has enzymes. All they do, all day long, 24 hours a day, is they search your genome for uracil. And when they find it, they cut it out, and they replace it with cytosine. And that's all they do. That's it. And the reason that is the case is because cytosine is stupid. There's no reason cytosine should be in our DNA. It's dumb. We should have gotten rid of cytosine and kept uracil. And here we are. Thanks, evolution.
Yeah, I guess that technique's the intelligent design model.
Yeah, and it's not, so the argument, and it's not, I want to be clear, it's not a this is bad design argument. The argument of why that whole thing supports evolution is it says, based on what we observe right now, that explains it, right? Yeah. That is a mechanistic explanation for why the genome works the way it does, right? It's an affirmative case. It's not saying, oh, well, that's stupid bad design, therefore intelligent design is wrong. It's saying evolutionary processes explain this thing that otherwise doesn't make sense.
Yeah,
it's so cool.
My favorite one, before we go, my favorite one that I've heard is a giraffe one, that thing in the giraffe's neck, everyone's neck.
Oh yeah, the recurrent laryngeal nerve. Yeah, right. Because it loops in that one little, it loops around that artery. So in most things, it doesn't matter because it goes here, it loops and it's back and it doesn't matter. But in a giraffe, yeah, it loops all the way down. So it goes down the neck and then back up the neck. Yeah. By the way, I just put in the chat on YouTube, there is a paper on this cytosine and uracil thing. It's called Confounded Cytosine with an exclamation point. That's actually the name of the paper. And it's one of my favorite science things that's ever been written. Yeah, I just love it.
Aaron, a second. I will make you a moderator so you can put a link in there if you need to.
Oh yeah, I'll just Google it real fast and put a link in there. It's such a fun, I mean, I'm weird, but I think it's a fun read. By the way, I saw somebody had asked about favorite or best books on evolution. I always recommend to people a book called Your Inner Fish by Neil Shubin.
I have that book on Audible.
It's wonderful. It's it's very accessible. It's not overly technical, and it really does a great job. Neil Shubin just does a great job of making these connections in terms of the showing how, you could look at how limbs develop in fruit flies, and that tells you how limbs develop in mice and humans by extension. And it's just like, why? Why does that work? The answer is evolution. Is why that works. It's a great book. This book, Your Inner Fish. I cannot recommend it enough.
Oh yeah, yeah. I watched I watched the 3-part series on whatever channel it was, like on YouTube or PBS or whatever it was, Discovery. The
I have not watched.
Inner reptile, inner monkey. I think the different.
Right, yeah, it goes. Yeah, I love it. I mean, that's one of the fun things with like evolution phylogenetics. Is like, yeah, we're humans, we're apes, we're monkeys, we're mammals, we're
Tetrapods.
fish. We're tetrapods, we're fish, we're chordates, we're this, that, the other thing. It just goes all the way up.
Yeah,
I love it. Yeah.
Before you had to go, I never knew. I knew some of the steps, but I never knew there were so many steps between fish and actual tetrapod. Or between mammal and amniote.
Oh yeah, right. There's the ancestral amniotes, and and you could just slice it finer and finer every time. You specialize and just zoom in.
I knew about synapses, thorapsids, and cyodots, but there's still so many between those things.
That's about where I'm at. Like, I got those. I got reptiles, I got mammals, and like that's what I got. The specialists, the people that really know this stuff, man, there's so many levels in there. It's really cool. It's so cool.
So you want to advertise? You have a Wednesday show every Wednesday or so often. You want to advertise your show?
I have an irregular schedule. I used to be a lot more regular in my schedule. I only started my channel back in, God, I don't even remember, May, June, sometime in there. I used to be a lot more regular. But then what happened was my wife and I had a baby, our second, in August, and then
kids can do that.
And then my family leave ended in October, so I went back to work. And I teach biology at the college level. So I do a lot of video recording and producing these days, but it's all for class instead of my YouTube channel. But I try to do stuff once a week or every other week. A lot of what I've been doing lately is more like this, kind of streaming and collaborating rather than like recording and editing stuff, because that just takes a lot more time. But my channel is Creation Myths. It's just Creation Myths. And it's all about basically taking creation science, young earth creationism, like at face value as science, and let's just examine it as science and show that like none of this makes any sense. It's just completely unconnected to like how things like population genetics actually work. Bears no relationship to reality. But we're going to approach it like we're actually going to do the math, and we're going to show that these hypotheses do not work. Like, I know I'm sure this is great marketing, but like a significant number of my videos, like we do math, which like, come watch my videos. There's math, right? It's really good marketing, but like, that's what it is. We're really going to treat this as science and see how it holds up or doesn't. And the answer is it doesn't. So that's what I do. And
I tried to have schedules if I can help it, but I like a few years ago I tried to have at least once a week, but that turned out to be a little, especially when I didn't have really regular guests, and sometimes I had to make up stuff on my own just to get a product out there. Like, so it burnt me out a little bit.
I know the feeling. Yep.
Yeah. Well, I'll let you go to bed because you have to keep.
I'm going to go to bed, everybody. It is my bedtime.
Yeah. So, before we go, do you have a catchphrase you say at the end of your videos to say goodbye?
I always tell people to don't get fooled. Don't get fooled.
Right.
That's it.
As I always say, never stop learning and enjoy the randomness. We'll see you next time. Bye.
Thanks, everybody.
If you just do it, it'll turn out okay. Hey guys, back to More Talking Time with Caffeine. You knew one of my guests from the last episode, Dan Creation Myths, but I also got a new guest today. Introduce yourself.
Hey everyone, I'm David Neff. I will be studying biology at the University of Maryland, Baltimore County in fall of 2021. I am super excited for this chat because ERVs are some of my absolute favorite subjects in molecular biology and genetics. It's so much fun. So I've been looking forward to this for quite some time now.
Oh yeah. So last time Dan was here, we talked about viruses and stuff and how they work and how to fight them and how they attack the body and attack cells. But what would happen if if the virus stayed around and say we gave the virus to our kids and our grandkids?
Now we're just stuck with it, and you do that enough times and you end up with 8% of your genome being the leftovers of dead viruses, which is where we are right now. We are more dead virus than we are human protein encoding gene by a large amount because of these things called endogenous retroviruses, which is so darn cool.
So a virus decides to attack, say, the thing that makes sperm cells, or the sperm cells itself, or the egg cells itself, or
basically, yeah, it has to infect the germline, and then a descendant. So the germline within your body, the germline are the cells that make either egg or sperm, and then a virus has to get in there, and specifically a retrovirus, so a virus that integrates itself into your genome. The way retroviruses work, they're super weird. They're RNA rather than DNA. So our genome is DNA. Retroviruses have an RNA genome, but they do this thing called reverse transcription. They go from RNA back to DNA. And we call that retrotranscription because, like, normal transcription is DNA to RNA. That's what we do when we express genes. Retroviruses go the other way and then cut a little hole in your genome and add themselves, and they just stick them right in there. And when they do that in a germline cell, you could pass it on to your kids.
So like, unlike regular viruses, they didn't like attack the cell and destroy it. They build themselves in there like a little like piggyback or something.
They can do either. So they can. So probably the best known retrovirus is HIV, which very famously attacks the cells of the immune system. And so what it does is it will get in and it will do the normal virus thing of get in, take over, make more of itself, and then burst out and go attack other cells. But that's not the only thing it does. It also can get into cells and kind of go into stealth mode and just integrate into the genome and just hang out. And for that reason, that's the reason we can't cure an HIV infection right now, or at least not typically. There have been a few cases that maybe, but those are exceptions. What happens right now with the really good HIV drugs that we have is that you can prevent any viruses from being circulating in the system. But what you can't do is cut it out. So if a person who is HIV positive was to stop taking the medication, then those integrated viral genomes could, in theory, reactivate and then cause illness. So they're in there. They can do the normal virus thing, but they do this extra thing where they just hang out and transmit as part of the host DNA, which is weird and opens up a lot of interesting evolutionary dynamics that most viruses don't have.
Okay.
And what I particularly love most about ERVs is that we can construct a phylogeny, an evolutionary phylogeny based upon endogenous retroviruses, and it matches perfectly from what we would expect from other methods. So it acts as a independent confirmation for what we already know from other fields of study. And I am pulling something up right now that demonstrates just that.
Cool. And also ERVs, I guess they had to, I'll say it, lucky they have to hope that the person they affect is like is someone whose genes death spread with the rest of the community, or that virus's line is dead too.
It leads to some really interesting evolutionary dynamics, because once you integrate, you're now kind of at the mercy of your host. And if you kill your host, well, now you're done. So it's actually what we actually expect to see is selection to minimize the damage done once the integration has occurred and you've kind of gotten stuck.
Yeah, so here's the phylogeny that I basically found based upon endogenous retroviruses. This is from the talk.origins website. 29 evidence from macroevolution, their study on endogenous retroviruses. Very interesting how we can actually do this. We see that humans and chimps are the closest relative, exactly what we already know from DNA sequencing, et cetera, et cetera. So this is very powerful evidence for common ancestry.
All right.
Yeah, it's super cool. It's super cool. And to put some numbers on that, with humans and chimps, there are about, and I'm using approximate numbers here, but there are about 200,000 retroviral insertions in humans and chimps, and like in each one, and over 99% of them are shared between the two. You can look at a specific place in the human genome, find an insertion in ERV, endogenous retrovirus. You look at that exact same place in the chimp genome, you find the same viral insertion. It's just beautiful the way it shows the pattern of common ancestry. It's really cool.
So what are the YC people that say that it's not a good concept for evolution? The virus could attack the same animal twice, different animals twice.
That's wrong, because we can actually watch in real time how these viruses target the genome. So, like with HIV, for example, we can document in people with HIV where the insertion sites are, and what creationists will say is, well, they have specific sites that they insert at. That's not true. They have preferences, and I'm using preferences. It's not. They don't have desires. They preferentially will target certain parts of the genome. HIV, for example, tends to integrate in gene-rich parts of the genome. But if you look at where HIV integrates, it integrates all over the genome, many different sites spread out on every chromosome in the genome. There's no one or handful of places where HIV integrates. That's true for other retroviruses as well. So you can find what we call hot spots and cold spots, where insertions are more likely or less likely, but it's not deterministic. So if you find two endogenous retroviruses with the same sequence in the same place, the best conclusion from that is common ancestry. And when you find 100,000 of them or 200,000 of them in the same place, that's common ancestry. There's no way around that.
Like,
exactly. It's kind of, it'll be like at the end, if you gave your students a test and you had 500 students and only 2 people have the same exact error in the same exact location, you could probably conclude that one is copying from the other.
Something funky's going on there. Yep. Mm-hmm.
And I'm sure you've seen a lot of, and I'm sure as a professor, you've seen quite a bit of that.
Less than you might expect.
Yeah, well, that's probably because you're at Rutgers and not some local community college. But
I don't know. You get some of the worst cheating scandals at places like I won't name any names, but
yeah, true.
Ivy Leagues.
Let's take a look at some of the.
Real fast.
Go right ahead.
How far back can we trace ERVs? Can we trace it? Do we share any ERVs with our plant or fungus cousins that we know of?
Yeah. I don't know of any that are shared among like major eukaryotic groups, but within animals, I know you can find a bunch. I know certainly with tetrapods. Trying to think. Mammals definitely, because then you could find mice ones that are homologous. I'm not sure how far back you can go actually. They do degrade over time, so you can actually look and see, like, for example, all ERVs have like a specific structure to them where they have kind of end pieces and then they have specific genes and stuff in the middle. And you can see that the ones like that humans have on our own are more complete than the ones we share with chimps, than the ones we share with chimps and gorillas, and so on back. The older they are, the more degraded they are. And most of the ones in our genome are just the end pieces. All the stuff in between has been degraded away. I'm not sure how far back you can go before that signal is gone, but I know that we can identify orthologous ERVs within different mammals. I don't know beyond that off the top of my head.
I guess also since mutations can happen too in the virus, so they might change after they split too, maybe.
Yeah. Mm-hmm. And once the changes happen in the virus that inactivate it, now you've removed the selective pressure to maintain it, right? Because if the virus is active, the ones that can propagate the most effectively are going to be maintained, and the ones that can't are not, because they're competing with each other. Once a virus is inactivated, well, now you can't, reactivate out of the genome. You can't keep doing your thing. Well, that removes all the selective pressures to keep all those genes active. You inactivate one of them, and it removes the selection on all of them. So now you're stuck in the genome with nothing keeping you there, no selection to stay complete. So when the host, either through problems with replication or recombination, or there's some evidence that there's enzymatic targeting of these things by the host because, like, aha, virus, kill it, right? When those things happen, those losses accumulate because there's no selection to keep that virus there. So you would expect to lose that phylogenetic signal over time. I don't know how far back you can go and still detect it.
All right, so what are you going to say, David?
So I kind of found a couple of creationists' rebuttals to the ERVs, and oh boy, is it bad. Here's one of the actual arguments. Interpretation. However, we know that the evidence doesn't speak for itself. Part of the scientific method demands interpretation. Since every science has to interpret the evidence, their interpretation bias affects what they say about origins. So ERVs, in and of themselves, do not prove evolution any more than they prove creation. Since we know that the word of God is true, we know that ERVs cannot be proof of evolution. And they go on and say, ERVs are not junk, which is basically standing for truth's reply that they have function, therefore they're not evolution.
I actually did a little work on that one, and there are a couple of functional groups of ERVs. Let me pull it up here, so I don't remember the numbers off the top of my head. But there are some functional groups of ERVs, and I wish I could find it here. I have too many things open. What else is new, right? Hang on. I'll find it. Here we go. So there are some that are involved in regulating human gene expression. That makes sense because ERVs contain promoters, and retroviruses often integrate in gene-rich regions. So that makes sense. We've co-opted several of those promoters. We know that they are used targeting for, like, the organization of the genome within the nucleus. That makes sense because you've got these regions that are kind of not doing much else. So you could be like, aha, let's use this. And then the other one, and my favorite, is when we have actually co-opted the genes. And my favorite example of that is genes called syncytins that are used during the early development of the placenta. These are genes that have been acquired from retroviruses. They're not technically active ERVs. They are genes that are under control of, like, human promoters, but they were acquired from a retrovirus. And these genes make a protein that is basically a stealth mode protein. It suppresses an immune response. Or I should say, specifically, it suppresses the inflammatory response. And this is important because it allows the embryo to implant into the uterus more successfully. So you can compare between the marsupials and the eutherians, the true placental mammals, right? So we're eutherians. Marsupials make a rudimentary placenta, but their young are born very, very underdeveloped and have to finish developing in a pouch, think like a kangaroo. The reason for that is the uterus actually mounts an immune response to the implanting embryos and kicks them out relatively early in the process. But with the help of these retroviral genes, suppressing that inflammatory response, you're able to develop a much more robust placenta that allows for complete development in utero in eutherians. And that wouldn't be the case if we didn't have these genes from the retroviruses. So, like, super cool.
Oh, another lame joke. Does that make Australia? Does this make Australia the origin of Pokemon, the original pocket monsters?
I get that joke. I get it. It took me a, but I get pocket. I get it. I like that.
Oh. So
go ahead.
So on the picture that David shared earlier, I noticed there wasn't any ERVs in the New World monkeys. Do we don't know about them, or there was none?
Huh, that's a good question. I'm not sure. I'm going to Google that real fast because I honestly don't know. I believe I would think there are, but I don't know. Well, actually, I will say this. I don't know if there are any New World monkey specific herbs. There should be. But in that figure, I think there were ancestral ones that it would imply that they would be in the New World monkeys, but I don't let's see. New World. I'm going to just Google New World monkey exclusive herbs. Let's see what we find. I don't know.
I think that was just that chart was just saying our. I guess that chart they were showing was just showing what we share of other the ones we share of other primates or other monkey, catarrhine, river, however you pronounce it.
Let's see. Yeah, it looks like they have them. Let's see. Genomes of all so all vertebrates have herbs. So that's first thing I just found. This is a paper from 2018. All vertebrates have herbs. So that answers that question. Let's see.
Sorry, chordates, you're out of luck.
Basal chordates. I mean, you would think, right? But I want to find a phylogeny of herbs among the Oh yeah, it looks like let's see, there are the primates, there are the lemurs. Yeah, it looks like there's herbs in all of them. Yeah, I mean, yeah, I'm sure they have their. I mean, they have to have their exclusive herbs. I don't know anything about New World monkey herbs, but they have to.
Yeah, that's totally why they came to the New World, escape from new viruses. That's why they came to get rid of like not we're not getting new viruses. Let's go escape to South America.
Right. Yeah, it's so let's see. So by the way, here's just so everyone's on the same page. The way we know these are viral inserts is very cool because retroviral genomes are super unique. They have 3 basic kind of components, and each component contains a number of different genes, but the components are GAG, G-A-G, POL, P-O-L, and ENV, E-N-V. Right? GAG, POL, and ENV. And each of those has multiple genes in it. And there's also a promoter in there. And the genetic structure is weird, and you express a polyprotein and then cut it. It's weird. Doesn't matter. They've got these three regions, right? And then when they insert, you also get LTRs, long tandem repeats on either side. So you get these LTRs with the genes in between. And then they do something really distinctive when they insert. When they land in your genome, wherever they cut, they make a copy of that. So if you have like a gene and then like a specific sequence, and the one I just happen to know there's an example in chimps where the kind of duplicated I think it's ATTAT. It doesn't matter what it is. Just give you an example. ATTAT. And then in humans, it's like gene, ATTAT, or region, whatever it is. You've got regions on either side that we can match to the chimp genome. And then we've got ATTAT in the middle. In the chimps, you've got region 1, ATTAT, LTR, GAGPOL, ENV, other LTR, ATTAT again, and then the region that matches to the human chromosome, right? So you've got these 2 regions in humans that are right next to each other. In the chimps, they're split apart. The region in between, that little bit is repeated on each side, and then you've got that retroviral structure in between. And that's like textbook retroviral insertion that's unique to the chimp lineage that's absent in the human lineage. And it's like you find those structures, whether it's the whole thing, some combination of those parts. Most of them are super degraded, and it's just the LTRs. Like, you find any of that stuff, that's a retroviral insertion. It's like, we know what these look like. We can watch them happen with things like HIV and other retroviruses that are circulating right now. We know what the insertions look like. So do these come from viruses is not an open question. ERVs come from viruses. They are the remnants of dead viruses that now make up 8% of the human genome. It's so cool that we could find that.
Hey, do we know if there's any viruses, different viruses, like within the human population that some humans have that others don't? Like
Viruses
like
that humans have?
like when we spread out out of Africa in different locations.
Yes. There is, I think there's one ERV that is variable among humans. So some human lineage, I forget where geographically and what lineage have what, but if you survey all of humanity, there's one ERV that some lineages have and some don't, and there's variation in the copy number. So a lot of times these things, when they mobilize, they'll cut themselves out. Instead of just spreading throughout the body, they'll just reinsert themselves somewhere else in the genome. So you get one copy over here, it copies itself out, but then just pastes itself down over here. So you get multiple copies in the genome. With this one particular ERV, you get variations in copy number, and some human lineages don't have it, which tells you that this is something that has been mobilized. It's been active in terms of copying itself and cutting out and inserting somewhere else, like since human diversity like split from our most recent common ancestor, which is super cool. Now we're talking within the last 200,000 to 300,000 years, these viruses were actually active, which is so darn cool that we can see that.
Probably say the same thing. Like we've at least traced our Denovian and Neanderthal cousins' DNA too. Do they have viruses that we don't have too?
That's a great question. I'm sure they do. I would expect them to. It was probably fewer than separate us from chimps, because you're talking between a few 100,000 years and a couple of million years for other members of genus Homo versus, like, on the low end 6 million years, on the high end 12 million years for the chimp lineage.
Yeah,
so I'm sure there are. Yeah.
At least the viruses that we didn't like breed back into us after we split.
Sorry, say that again.
At least the viruses that we didn't breed back into us after the split.
Right. Yeah. I mean, it could if it was in the germline, you could potentially see that happening. And I don't think there are any associated with the Neanderthal markers that we've identified, but I can't say there aren't for certain. I don't know of any, but I can't say there aren't. Be an interesting question. I don't know. Something to look at.
Any input from you? Look, David, you there?
Yeah, I'm there.
Oh.
Trying to think. So yeah, we can actually look at the human ERVs as well and use that as a phylogeny and see, okay, can we trace human origins back just by ERVs alone? And what do you know? It matches up perfectly with what we'd expect.
Can we actually do that? That's super cool. I didn't realize we get that tight resolution on there.
I'm not sure how precise it is, but I'm pretty sure I saw something similar to that. See if I can find a paper real quick.
While he's looking, like whenever he's getting into our sperm and egg DNA, do they replace the like do they replace whether in there or they just insert themselves? Like,
they insert themselves, and it's actually not just ERVs, but also retrotransposons and DNA transposons. These are all classes of what people broadly call mobile genetic elements. It's things that basically cut and add themselves, and then they can make a copy and go over here and add themselves over here. And the transmission of these things is thought to be one of the major mechanisms that drives the increase in size of genomes, because it's kind of a ratchet where once it's in, unless you have a targeted mechanism to clip it out, it might degrade over time, but I mean, it's there. And so it inserts, it adds itself. It's going to, it's a copy and paste. It's not replacing stuff. It's inserting. And over time, you end up with a huge portion of the genome that's these things. So ERVs are about 8% of the genome. And you've got other transposons, DNA and RNA, that are even bigger than that in terms of percentages. I think altogether, they make up something in the neighborhood of 45% of the human genome are these transposable elements, most of which are now inactivated. They've mutated and they're now stuck. They can't mobilize anymore, but the remnants are still there, and we can tell what it is based on the sequence. So you get this kind of ratchet effect where they integrate, they add to the genome, they'll mutate over time. Many will be inactivated. Some will acquire functions in that new position in the genome. But most just kind of sit there and hang out. And I'll say that many are actually targeted for inactivation, and it's thought that that is part of the immune system, where if everybody's familiar with the concept of methylation, if you add methyl groups to the DNA, it inactivates it. And one thing that we think is kind of underlying methylation patterns across the genome is that we have these things like transposons and retroviruses that we don't want to be active, because they'll mess with your cells if they're at the very least they're taking resources.
Yeah, especially since when you pass them to their kids, when you pass them to our kids, they're in every single cell that kid has.
Yeah. Right. So it's beneficial to have a mechanism that shuts them down. So we have enzymes that go around and methylate the crap out of these areas. And you'll see creationists that'll say, well, that's evidence that it's functional because, it's specifically targeted for these things. And I see that the other way around. If you're methylating something and just causing it to condense so it can't be expressed at all, that's really strong evidence not only that is not functional, but that if you allowed it to mobilize, that may actually cause a problem.
Yeah. So once it passes on to the kid, is the virus dead in our descendants, or can it be reactivated once it's been passed on?
It depends. So most of them are like dead as a doornail because they've mutated and they've lost stuff, right? So you need an enzyme that's able to cut it out. You need an enzyme, you need a sequence to say, copy me, right? And then you need the reverse transcriptase to be able to do its replication. So if it loses any of those components, then it's dead. It can't do anything. But there are ERVs that are like complete enough that it could mobilize, and we do actually see some evidence of this where when there are problems with DNA methylation and like targeting retroviral sequences with methylation and other forms of inactivation, we do see increased transcription from these areas, and that's actually associated with various forms of cancer. So it's possible that we do. I think it's likely that most of them are like dead, and of the ones that are not, we do a really good job with our immune system of shutting them down. Right, we target those regions to make sure they're not messing around. But sometimes there's a problem and they do mobilize, and there's evidence that is associated with various diseases. But that's a small fraction. There's relatively few that are complete enough to be able to cause a problem.
I was thinking tracing viruses and stuff, and what Dave's still looking. Do we know of any? I know viruses mutate, so it's hard to have any ERVs in our bodies that match with viruses that we know of nowadays and out there.
I don't know of any endogenous retroviruses that are really good sequence matches to circulating retroviruses. but I just don't know enough about it to be able to tell you yes or no. I know I think there are 3 classes of endogenous retroviruses, and if I had to guess, they probably have like common ancestry with a specific group of retroviruses, but
Okay.
I don't know enough about the specifics of them to be able to tell you.
I was wondering,
Yeah,
I was
sorry.
wondering since we could, I was just wondering if because we could trace back that chloroplast match cyanobacteria and our
Right.
mitochondria match the whatever bacteria they match.
Right. Yeah.
I was wondering.
Could we do that? Well, I'm looking it up because I wonder if we can. Yeah, there are 3 classes, and actually, it looks like they are. Just gonna look at. Let's see. I don't know if they. Okay.
So, like you, David, if you
Yeah,
found,
I don't know. I don't know off the top of my head if they're similar enough to circulating viruses to be able to say they came from this group of retroviruses. I wouldn't be surprised, but I honestly wouldn't be surprised either way.
Okay.
Because they mutate retroviruses mutate relatively fast. So think about like HIV. It's hard to we don't have a vaccine against HIV because it one of the reasons anyway is that it has a relatively fast mutation rate. So even within a single person, you have enough variation within that population that a vaccine may only be able to target a small fraction of it. Given that, that means your phylogenetic signal is going to get pretty messy pretty fast.
And viruses, especially HIV, is perfect case against genetic entropy, the one of the worst creationist arguments in the book, because they would be extinct by now, given how fast they mutate.
It's true.
It's
true.
You remember last time you were here, we talked about bacterial phages and stuff.
Mm-hmm.
Right. I heard there's some viruses that attack other viruses.
There are. Yeah, they're called virophages, and they are relatively small viruses. And they basically parasitize enormous viruses. In a group of viruses, I'm going to say the whole name because it's fun. It's the NCLDVs, which stands for nucleocytoplasmic large DNA viruses, which is a mouthful, but it tells you exactly what they do. These are the big viruses. These are Mimi virus, and Mimi virus was the first one we found. It was the biggest virus for a little bit. Now it's like, I don't even think it's on the top 10 anymore. There's just tons of diversity in this group. One of them is Pandora virus. Another one I think is Medusa virus. Now we're naming them after Greek mythological characters, which is fantastic to me.
Yeah.
And these viruses infect amoeba, and they basically just take over the whole inside of the cell and make a big structure called the viral factory. So it's the Mimi virus factory or the Medusa virus factory or whatever. And these little viruses, these virophages, they can infect the amoeba as well. When they infect on their own, they don't do anything. When they infect at the same time as one of the big viruses, so you get the little virus and the big virus in the same cell, that Mimi virus factory, instead of churning out more Mimi viruses, it gets hijacked and turns out the little viruses instead. It's so cool. So it's a virus of a virus. It's called a virophage.
So too bad we can't find a viral phage for the HIV virus.
Yeah, right. You need to be really complex to have a virus that infects you, and HIV only has a handful of genes. Like I want to say 10-ish, but someone can correct me on that. Whereas these Mimi viruses, these giant viruses, have over 1,000. So they basically do everything for themselves, including a lot of things that viruses aren't supposed to do for themselves. The big viruses do for themselves. So a little virus can take advantage of that. They're opening themselves up to being parasitized by being so complex. Whereas smaller viruses that have fewer genes, there's nothing to parasitize.
Yeah, so it's like a big food chain. The bacteria attack the viruses, attack the bacteria. The other viruses attack the virus, attack the bacteria.
Yeah, and you could actually see this in Antarctica. I think it was. Was it Antarctica? It was somewhere there was. I forget if it was Antarctica or somewhere else. I want to say it was in Antarctica though, where they found there's a lake, it had algae, and the algae had a big algal bloom, and then the algal bloom all got infected by one of these giant viruses, and it killed most of the algae. But in the middle of this outbreak, where the algae are getting destroyed, all of a sudden the viruses, the big viruses, start getting killed because the outbreak of the giant viruses led to an outbreak of the virophages that killed all the giant viruses, and it let the algae come back up. So you had this circulating rocks, paper, scissors game, basically, of algae, giant virus, virophage within this lake. It's a very cool dynamic, very kind of multi-tiered, complex ecological system. Kind of oh, David, was that you?
Yeah, sorry, I was echoing in the background. I was trying to pull up the video in the tab so I can make a quick comment here.
So you found some new information for us?
No, I was responding to the person in the sideboard chat.
Oh, what happened here?
Oh,
okay. This person has to be a Poe. There's no way.
Yeah,
There's
I know.
no way.
yeah. He's been.
Actually, this actually
There's
does
no
lead,
way.
this actually does to a real question, and that is at the beginning of the COVID pandemic, there were some conspiracy theories about COVID being lab made. If it actually was lab made, if there were a virus that was lab made, what would we actually expect, if that's even possible at all?
I mean, it's certainly possible. I mean, there's viruses as bioweapons is a strategy that goes back to, like, I mean, we didn't know what we were doing, but I mean, you can go back thousands of years and find like the stories of like catapulting, smallpox infected bodies over a city wall or something during a siege. But in the modern world, that looks like trying to take a pathogen of some kind and optimizing it for both transmission and mortality, which is not an easy thing to do. The U.S. has a bioweapons, or had a bioweapons program. I'm sure we still have all the stuff, although I don't off the top of my head know how active it is. I'd assume it's still active. Lots of places have bioweapons programs. But with SARS coronavirus 2, you can do the phylogenetics on this virus. It falls out. You do a big phylogeny of coronaviruses, and you get one clade that's all the bat coronaviruses, and then right in there, nested within all the bat coronaviruses, is SARS coronavirus 2. It's not hard. If it was a bioweapon, it wouldn't look like that. It would be different.
Yeah.
Right.
Oh,
So,
speaking for like that, are either of you eligible for the vaccine yet?
I am not, unfortunately, but I hope to be soon.
Okay.
I am already vaccinated because I was actually in the Pfizer clinical trial, and I did not get the placebo. I got the real deal.
Awesome.
So
I'm
I
sure-
got that. I was unblinded a couple months ago, and I'm gonna print that letter out and stick it to my fridge because heck yeah.
Cool. Yeah. I heard they're going in the 50s and up pretty soon, so I'm getting closer. I'm the 40 and up range.
Alaska just opened it up to everybody over 16. Just today.
Time to move to Alaska. Just kidding.
That will be more of that soon.
Yeah, I heard.
The supply is greatly increasing.
I heard in New York they had to start IDing people because people out from more people were getting the virus that were even live in New York that were.
That doesn't surprise me at all. Yeah, I mean, at this point, we're getting to where we're going to have such a surplus very soon, within a couple of weeks, that it's going to be opened up to everybody relatively soon.
Yeah, and hopefully Biden actually is able to get his goal of millions of vaccines in his first 100 days. And if we're
already over 90 million.
Yeah, if we actually do what the CD says and everyone gets vaccinated, we can have this thing beat by the end of summer.
Yeah, easily. Yep. Oh, easily.
I wonder if the COVID virus attacked anyone's germ cells.
It does not integrate. It is not a retrovirus, so we don't have to worry about it. It is an RNA virus, but it's not retrotranscribing, so we don't have to worry about that.
Okay.
One thing we don't have to worry about: persistent infections, which is good.
Yeah, and I'm also glad, at least that they're aware of. I might have to let them that it's not one of those mosquito viruses either.
It is not a vectored virus. Yes, thankfully. That would be, that's a whole other thing. But on the upside, that actually opens up other avenues for attacking the virus. Because, like, if you kill the mosquitoes, no more virus. So that kind of goes both ways, right? So, like, malaria is not a virus, but it's a mosquito vectored parasite. And going after malaria is hard because it's resistant to most of the drugs now. Or at least most malaria instances are at least partially resistant to various treatments. Many still work, but it's dicier than it was, say, 40 years ago. But if you can kill the mosquitoes, and we have things like CRISPR and gene drives that we're gonna start doing that soon, and I'm really excited. I am fully in favor of killing all the mosquitoes. Kill all the mosquitoes.
Yep, I agree.
Yeah,
They're evil.
yeah. This guy, I see him in other videos too, like Dapper Dinos and Erica's videos. His propaganda, this chat doesn't nothing to do with the subject.
I mean, can I block him?
You want to?
Yep.
We're gonna use a timeout.
Yep.
And then we'll see what happens.
Yeah. Like I first saw him in one of my videos about. I was doing a video about not even about science. It was about fan fiction, like a video game fan fiction. I was interviewing this guy who wrote these stories about these video game characters, and here he comes talking about flat Earth and evolution is wrong. I'm like, good for your stupid opinion, but that doesn't do the stuff we're talking about.
Yeah, not even the venue. I draw the line at like COVID trutherism and propaganda. Like,
same here.
If you're anti-vaxxing, I'm goodbye, delete.
Yeah,
see you later. You're blocked.
I will say this: anti-vaxxers are murderers. Point blank. If you're spreading deadly disinformation about vaccines, you're a murderer. Plain and simple.
I guess there's 3 levels of stupidity. Not stupid. There's the YC people, then there's the flat earthers, and then there's the anti-vaxxers. Top of the list. And usually they're all the same. Usually they're all the same people. Usually some are other ones, but usually the anti-vaxxers are also like Kenny here is also a flat earther, and if you're that far in there, you're probably all 3.
The thing so people actually often ask, like, Dan, why do you bother with creationists? What harm does it do? They're going to say that the world is sick. That who cares? Real scientists don't care, right? Like, and that's true. The problem, as I see it, is exactly this, because if you can train your brain to believe something that is clearly not true, that is in conflict with all of the available evidence we have, if you can train yourself to believe that thing anyway, then you could just as easily train yourself to believe something that's harmful, like anti-vax, as you can something that's relatively harmless, like young Earth, right?
Yeah.
It's the same mental exercise, the not just losing the ability to critically evaluate information, but practicing undoing those skills and being actively able to reject good information and actively unable to reject bad information. Like, it's the same set of skills, and if you train your brain to do it for one thing that's silly and harmless, then that can have harmful consequences down the road, and that's the problem.
Yeah.
And at the same time, you can cut that off if you can train. You can teach critical thinking, and you can, like, how to evaluate data and how to actually, like, evaluate scientific hypotheses. You can apply that to something that is not controversial. Those skills carry over to other things, whether they are harmful or not.
Yeah, I used to say this a little bit. Sometimes I give the YCers sometimes that aren't like doing this on purpose, for money, the benefit of the doubt. Sometimes because they've only had to accept that evolution is a thing for like maybe like 100, 200 years now. Flat Earthers had to accept the deal like almost 2,000 years at this point.
Flat, yeah. I got nothing for flat Earth. We literally have pictures of the planet of Earth taken from outer space. We literally have pictures. I got nothing.
They've been
Yeah, the thing with-
photoshopped.
I
Yeah.
mean, I can look at the moon and see the curved shadow on
Yeah,
the
the other
moon.
thing of
It's curved, guys. It's not
Exactly.
a line.
yeah, the other thing with young Earth creationism is that it's a special kind of pseudoscience that it is refuted by literally every single fact of science. Like there is not a single fact in any field of science that gives even an iota of credence to young Earth creationism.
Yeah, I thought it interesting, not the evolutionary thing, but abiogenesis and stuff. We're going all over the world, or we're jumping all over the place in these topics, but that you can that some of them might have formed in space through meteors and stuff.
Yeah,
Amino
and
acid.
we found like organic stuff like on meteorites. So it's one of the hypotheses, and it's not impossible. Yeah.
So have we found viruses on meteorites?
No, we haven't found anything more complex than very simple organic compounds. Viruses, you need something to help them, replicate, because they can't do it on their own. So you're only going to find viruses, at least as far as we know, in an environment where there are also cells. You're not going to find viruses outside of that, because they need something to replicate them. And even the biggest, most complex viruses, there's a few things that they can't do on their own. But I will say that it gets a little bit weird, because the definition of virus is not as simple as you might think. The simplest definition of virus is a intracellular parasite that transmits via, an extracellular capsid enclosed stage. But we can find plasmids that we've actually watched them in the lab adapt to transmit via little bubbles of fat called liposomes. And that's pretty darn close to a virus. It's like, well, what is that thing? It's a plasmid. We know what it is. It's a plasmid. It's a little circular piece of DNA you find in cells, mostly in prokaryotes, but not exclusively. Go ahead, Nev.
Oh, yeah. I pretty much don't really have much else to say.
Yeah. So these plasmids, we know what they are. We can and then in this one experiment in the lab, they found the plasmids like going between, you got a cell, you got another cell, and you got a plasmid that'll be like, I'm in here, and then it'll make a copy of itself and kind of blob off and move over to this other cell. It's like, you're not supposed to be able to do that. How did you do that? That's how viruses work, and you're not a virus, you're a plasmid. What just happened? And now we kind of the definition gets a little bit weird once you start getting into stuff like that. So,
yeah,
as in all things in biology, there are no hard and fast lines. There's just a wide swath of gray.
Yeah,
and that's where all the fun is.
So it's like it's probably hard to, if at all, the trace viruses through our phylogeny tree. If they're separate or connected to them, or whatever.
Yeah, right. Once it's part of our genome, is it a separate entity, and is it undergoing like a kind of selection on its own? And you see some really interesting dynamics. So once it integrates and it gets stuck, you would expect to see selection, not just to not hurt us, because it only reproduces when we reproduce, right? You expect to see selection to help us. And you actually do see this in some bacteriophages. So there are bacteriophages that infect cyanobacteria. And those bacteriophages, they can integrate into the genome. I think they're temperate phages that can integrate. But these phages have with them genes to increase the rate of photosynthesis. So when they infect a cell, that cell generates more energy for itself, basically giving the virus-infected cell a competitive advantage against the other cells in the population.
So if they can attack the cyanobacteria, can they also attack ones that are already chloroplast, or is that they protected inside the eukaryotic?
I don't think so, because I don't think they can get into the eukaryotic cells. I think they're limited to getting into the bacterial cells, and they can't get across the eukaryotic membranes, because biochemically they're going to be very different. Yeah. Although that would be really interesting, and I'm trying to think now. I am not aware of any viruses that infect plastids. But goodness, I wouldn't, now that you mention it, I wouldn't be surprised at all. And I actually know who to ask about that too. So that's an interesting question.
Nice.
Yeah, there's a whole subfield called cellular metagenomics. So metagenomics is when you just like survey from the environment and just like what DNA do you find? Just sequence everything and just see what you find. Cellular metagenomics or single cellular meta is when you take a single like an amoeba or an alga, right? And just within that one cell, sequence everything. And you find viruses and parasitic bacteria. You get your plastid DNA. You find all kinds of weird stuff in there. So I wonder if there's any phage in there that infects the plastids. That's a really interesting idea. And I've literally never thought of that until right now. But that is something I'm going to want to look into.
I started a new conversation out there now.
There we go. I want to look at plastid. I don't know what you call that thing. I guess you would call it a phage, right?
When a virus does, when a retrovirus does insert itself to a cell part of DNA, is that the same as endosymbiosis?
So a virus is different from endosymbiosis. Endosymbiosis, like the process, is when a big cell engulfs a little cell, and then that little cell, rather than getting digested, it over generations becomes a component of the larger cell. So you have predators that were eating cyanobacteria, and over time, those cyanobacteria, instead of breaking down, they became chloroplasts and other plastids. And so when a virus gets in, instead of and you could think of, I should say, we think of endosymbiosis, or we learned about endosymbiosis as like a partnership, but it's not that. It is a fight to the death, where the big cell is like, I'm going to eat you. And the little cell is like, no, you're not. And they're fighting within the big cell. And the equilibrium they arrive at is an organelle, right? A chloroplast, mitochondria, or whatever. With viruses, because when they get in, they break down. The first thing that happens is you lose the structure, right? The virus doesn't stay intact. So you don't have that same opportunity. So when viruses become part of the host cell, the way they do that is by integrating into the genome rather than staying as a discrete structure like you would see in endosymbiosis. Because when a virus gets in, you open up that capsid, you release the genome, like the viral particle that infects a cell then ceases to exist. It breaks down so the virus can do its thing. So there's no physical entity to become part of that host cell. It's just the DNA or the RNA is what matters. And then that happens all the time, right? That's 8% of our genome are those things that stuck around.
And some viruses are just RNA viruses, others are DNA viruses.
Yeah, they're everything. So you've got double-stranded DNA viruses. That's normal, right? We use double-stranded DNA. That's reasonable. Single-stranded DNA viruses. That's a little weird. Double-stranded RNA viruses. Also weird. We tend to think of RNA as single-stranded. You've got both positive and negative sense single-stranded RNA, which means is the genome mRNA directly, or is it complementary to mRNA? So you've got two different flavors of single-stranded single-stranded RNA viruses. Then you've got the retrotranscribing viruses, which I believe there are two groups of those. There's the canonical retroviruses, and then there's another group that does retrotranscription, and I forget exactly what those are called. But for anyone watching, there's a system of viral classification based on the genome structure. It's called the Baltimore system. And it's class 1, class 2, class 3, class 4, and it's based on the different genomic architectures. Yeah, and the fun part is that all these different groups and even different lineages within the different groups have independent origins. So viruses are massively polyphyletic. We're talking dozens of different origins, leading to all these different genomic architectures, which is super cool.
Right, and if young Earth creationism was correct and everything was in distinct, neat kinds, then that's what we should see.
Yeah, that's one of my favorite tests of universal common ancestry for cells, because cells all use double-stranded DNA and use it the exact same way, whereas viruses, which we know do not share common ancestry, what does that look like? Well, they have all different genomes. Like their genome structures are all different. Cells all have the same genome structure. Right away, that's really strong evidence that they're common ancestry.
Yeah. I think I mentioned this in the last episode about viruses that I always wondered if maybe if we had a common ancestor with viruses that split off, the viruses went one direction and the cells went another direction when we were still just doing our enabled hypothesis.
I think some viruses do. I think there are some groups of viruses that share common ancestry with cells, and others definitely don't. Like there's a group of viruses that infect plants that like we know they evolved from a specific group of plasmids. And like we could just do the phylogeny and you get this phylogeny of plasmids. And then in the middle of this, there's this one branch of viruses all on their own that are unconnected to anything else. Like, okay, well, we know where they came from. There's some people that'll argue that those big viruses I mentioned earlier ought to be like a fourth domain of life. So you've got your bacteria, archaea, and eukarya, and then you should have the viruses sticking off there. It's a whole big viral phylogenetics is just a big, glorious mess, and we don't have answers for a lot of it.
They probably mutate faster. Viruses probably mutate faster than the cells do.
Yeah. So you lose the phylogenetic signal really fast. So like even if there is common ancestry between some groups, after a couple 100,000 years, you're not going to be able to detect it anyway because you get what's called saturation, where any two nucleotides in these two genomes that's the same, the probability of being the same through convergence is equal to the probability of similarity due to common ancestry. And at that point, it no longer becomes informative in terms of their evolutionary histories.
Yeah,
so you run up against that problem.
You said convergence. Is that like some YCs say that the virus could attack the same place, different location?
When we say converge, we mean like it's like when you work backwards in the past, like how you have two different sequences, how given the mutation rates, how far in the past would they have had a common ancestor? And the problems for viruses are that they have such small genomes and they mutate so fast that like for humans, it's easy to like track that signal back because we get a big genome and slow mutation rates. For viruses with a tiny genome and fast mutation rates, that signal gets real muddy as you go back, even in the order of thousands of years.
Okay, I thought you should think conversion. I think like conversion evolution, like with dolphins and ichthyosaurs.
Oh, I see what you're saying. Yeah, exactly. So you could have different groups of viruses where you might have like a similar gene that ends up looking the same, not due to common ancestry, but it looks really similar because they mutate so fast and there's just not that many differences. Like there's not that many sites to mess with. So you can end up at convergence just by chance. And then your phylogeny is all messed up. It's what makes it's part of the charm of viruses. Is it's hard to figure out what happened.
They're clever little girls. Those viruses.
They're great. It's what makes it really is like you talk about like the origins of cells and go, okay, they had this, we kind of figure it out. The origins of viruses, and it's a huge mess, and it's great. It's so much fun.
Yeah, we may talk about animal and vertebrate viruses because that's us, and we like stuff that's like us. But is there people that study ERVs of like plants, how far they go back? They start plant ERVs. I'm
sure there are people that do that. I don't know at all of that field. My to the extent I have any expertise in endogenous retroviruses, it's purely among animals. I don't know about them in any other context beyond that. I'd be astonished if they didn't exist. But I don't know. I don't know for sure.
Like say if we can see a virus common between like say a daisy and an apple tree or something, or a seaweed, or I forget how plant phylogenies work.
Yeah, you would expect to find it like so. The four main groups, you've got your non-vascular plants like your mosses, and then you got your seedless vascular plants like your ferns, and then your gymnosperms, which are like seed plants but no flowers,
like pine trees,
angiosperms. And that's all. I'm trying to think. Plants, a couple 100 million years. They're actually that a lot of that diversification was post-Cambrian, so you get that actually more recently than a lot of animals.
Oh, yeah. So you got. It's been an hour, so you gotta go because of your baby's fever.
I should be responsible and get myself to bed at a reasonable hour this evening. So I think what I'll leave everybody with is endogenous retroviruses, super awesome, make up 8% of the human genome. And the really cool thing for evolution is you can follow the phylogenetic history of vertebrates just based on endogenous retroviruses. And you can reconstruct all the relationships just based on ERVs, which is so cool.
Yep.
Another layer to the puzzle.
Yeah.
Morphology, DNA, and now viruses.
Definitely a lot of fun. And that's why I'm studying biology.
The best subject.
Yep. I love it.
Before we go,
I
you
love
want
it.
to you want to shout out your show if you're on your show tomorrow or not? You want to shout it out?
Sure. So yeah, subscribe to my channel, subscribe to Dr. Dan, subscribe to this channel here, and I am planning a debate coming up soon with Gavin on the subject of the resurrection of Jesus. That will not be on Standing for Truth's channel. It will probably be on Praise's channel, but stay tuned. But it will definitely not be on Standing for Truth's channel.
Yeah.
So stay tuned.
Yeah, we're having a little issue.
I don't have anything coming up in the immediate future. I might have some.
Oh yes,
I might do a stream later this week or next week. But then the really exciting thing is March 22nd. I am having Michael Behe on to talk about irreducible complexity. That's going to be super exciting. That is March 22nd on my channel, Creation Myths, at 1 p.m. Eastern. Michael Behe is going to talk to me about stuff. Yeah. And
one thing that I am working on is a new series called Yuckfield. So basically, it's just a bunch of the funniest clips from young Earth creationists and poking some fun at them.
Okay, so I can have your. Oh, nice.
If you want, I'll give you a backstage.
Oh, awesome. So you're not going to have your usual Wednesday show tomorrow then, your baby, because of the fever and stuff.
Oh, I don't really have a normal Wednesday show. I just occasional. I don't know. I don't have anything planned for tomorrow. We'll see. Maybe if I do something, it'll be short notice. I don't have anything planned for this week though.
If you have,
I wish I had a regular schedule, but I don't.
Yeah, if you have time tomorrow, I would love to have you come on to talk about your PhD thesis and other stuff.
Cool. Yeah,
I will definitely do that at some point.
Yeah.
I don't know about tomorrow, but I will definitely do that because I will tell you. You ask anybody, what did you do research on, or what did you do research on? Oh, they will just go for a long time.
Oh yeah.
Get ready to talk about cytosine, my favorite thing.
Yeah. Well, join me this Saturday. I have no time yet. With me, RJ, and our friend Eric, we're talking about the drama of the drama. People, an uprising. People are creating it over the Dr. Seuss books.
Oh goodness gracious! Oh. Well, that'll be a fun one.
Yeah.
Right. Until then, check. I'll have the link to their channels in the description below. But in the meantime, never stop learning and enjoy the randomness. I'll see y'all next time. Bye.
Bye-bye, everyone.
All right. My opening catchphrase has so much more meaning today. If you just do it, it'll turn out okay. And by do it, I mean get the vaccine.
Get vaccinated, everybody.
Yes, please get vaccinated, protect yourself, protect your family, and most importantly, vaccines protect those who cannot be vaccinated. It protects the children, it protects infants, it protects those who are immunocompromised. So your decision to not get vaccinated doesn't affect just you.
Mm-hmm. Yep, and today we are going to be debunking some of the rumors that have been spreading out the internet about the dangerous vaccine out there. Like number one, the vaccine mandate that they're going to force everyone to get the vaccine. They're going door to door, giving it to you.
So before we get going, should we go around the horn, introduce ourselves?
Yes. Everyone knows who I am.
Yep. Well, I'm David. I'm a biochemistry and molecular biology student at the University of Maryland, Baltimore County. And I really enjoy studying viruses and vaccinations and evolutionary biology. So this is right up my alley. Thank you so much for inviting me on. And Dr. Dan, it is so good to see you again.
It's great to see you too. It's been too long.
Yeah. Well, the last time you two were on together was my ERV episode.
Yes. Oh, fun times. Always a good topic. I'm always here talking about viruses. What can I say, right?
Yeah.
So, hi, I'm Dr. Dan Stern Cardinal. But apparently the internet now just knows me as Dr. Dan. I do mostly anti-creationist stuff, but I'm an evolutionary biologist by trade, and my specialty is virus evolution. And I'm super pumped about mRNA vaccines. And before we go any further, just full disclosure about how enthusiastic I am about these. I was a participant in the Pfizer trial. So I got my shots way back in the fall. And then I recently crossed over into, just last month, into the booster trial. So I'm still blinded for that, but did that back in, I think, July at some point. So I'm not just like super gung ho about everybody getting vaccinated, but I'm putting my money where my mouth is, and I'm doing this, as part of the trial to make sure everything works the way it should.
Definitely good.
Yep, and the same note, Moderna is starting an mRNA vaccine for HIV, and I am working on enrolling in that trial. So hopefully I get accepted for the HIV trial.
Oh, cool! I can't wait to see that turns out, since that virus affects the immune system itself. So
that'll be. I'm hopeful that the mRNA platform will do it for that, because the problems there are both persistent immunity and then targeting as the virus changes. And if we can address one of those, it makes it easier to address the other one. So I'm really, not just for HIV, but for like lots of stuff, I'm super enthusiastic about mRNA vaccines going forward.
Yeah, you mentioned You mentioned mRNA vaccines during our first conversation about vaccines in general about a few months ago.
Yeah, I think this is my third round here, right? So yeah, we did vaccines, we did ERVs, and now we're COVID vaccine misinformation. And yeah, just to very briefly summarize, the way mRNA vaccines work is they introduce a small amount of what's called mRNA. It's the stuff that our cells use as the directions for making proteins. So the vaccines bring into your cells the directions to make the spike protein for SARS coronavirus 2. And our cells make the spike proteins, and then our immune systems recognize those spike proteins and go, aha, a virus. And then you make activate your T cells and your B cells, and you make your memory B cells and your plasma cells, and you make a bunch of antibodies in the first round. And then in the second round, you make a lot of antibodies, and they stick around for a long time. And what we're actually working on right now in the booster trials is just how long do those antibodies stick around and provide protection. So we'll go through a bunch of rumors, conspiracy theories, and misinformation that are circulating about these vaccines. Before we get going, there's one thing I want to say about this whole exercise, and it's discouraging, but I'm going to say it anyway. And the thing is that for people who are like hardcore anti-vaxxers, I don't think anything we're going to say tonight is going to change anybody's mind, which is just how it is, because it's about identity much more than it's about facts. But fortunately, there's kind of two groups of people, right? There's the vaccine hesitant, and then there's anti-vaxxers, right? And I think the anti-vaxxers are basically a lost cause. There's nothing anybody can say that's going to change their mind. But people who are vaccine hesitant, people who don't like follow scientific news day to day or week to week, people who just get their news from like the New York Times or whatever, or CNN, or even just like the evening news for people who still watch the evening news, or people who, God help us, get their news from Facebook of all places, right? It's a series of facts and concerns that have led them to decide not to get vaccinated yet. And I think a lot of those people may be reachable. So hopefully we could address some of those concerns tonight. I also do want to say when it comes to I just want to say when it comes to identity, there was a thing happen actually just today in Tennessee. There's a conservative radio host named Phil Valentine who for months railed against vaccination, and then he got COVID. And then once he was sick, he started saying, I screwed up. Everybody should get vaccinated. And it's that kind of thing that's going to change people's minds much more than what we're doing, because people that like tend to agree with us on stuff like science, they're already vaccinated, right? So it's people who are not in the same social circles as us, people who are not, the arrogant coastal elites, right? Like that's not the target audience. But this is not the most effective way to reach that audience. So we just have to be realistic about that. Now, the kicker for that story is that Phil Valentine died of COVID today. But what he was planning to do when he got back on air, had he recovered, was to be a strong advocate in favor of vaccination. And that would have made a difference had he been able to do it, right? And it's a shame that he can't do that, because that actually would have convinced people much more than anything I can say, right?
Right. And I think another reason why this is so important is that it helps arm people who are already vaccinated with facts and information that they then can go and share with other people by
100%.
learning. By teaching the people who already are vaccinated, they can then go and spread the word, so to speak, preach the gospel of vaccinations.
Yeah, that's an excellent point.
Yeah. It's too bad it takes something like that to convince some people, but besides, as I said before, some people like say example like Marjorie Taylor Greene, you mentioned her before, saying if they come with the vaccine, shoot them. That's what one of her speeches.
Yeah. So. Yeah, that's not reachable, right? There's nothing anybody can say that's gonna change those minds, right? But that shouldn't be the target for people who are pushing to get those vaccination rates up.
Yeah.
And I will also say that two big things are coming very soon. One is on Monday, we're expecting full non-emergency FDA approval for Pfizer at least. And that's fantastic, because a lot of people have said to me directly, like, emergency approval, let's not rush this, right? So now with full approval, that'll hopefully get some percentage of people on board. And then the other big thing that we're expecting September, October, I'm hoping more towards the September side of things, is kids down to age 5, which there's a whole big cohort that there's going to be a huge wave of millions of vaccinations once it's opened up to them. And then hopefully within a few months after that, we can get down to kids. I think I read it was down to 6 months would be the next cohort. And the hope there for me is by the new year, we can start doing that. And there's another, millions of people that'll get done once it's open.
Can I say something about the FDA approval? Is that I find that if they really considered the stuff that they take that's not FDA approved already, many of the multivitamins, dietary supplements, melatonin, and over-the-counter stuff that we take is not FDA approved.
Yeah.
So it seems like it's kind of like a self-contradictory, self-refuting argument, because there's so much out there that we already have no problem with that's not FDA approved.
Yep. So oh, go ahead.
Sorry. One of the things I on Facebook, Dan knows, a week ago I posted stuff on Facebook about the coming video. We got a lot of different reasons, and one of my favorite one was, "I'm not an anti-vaxxer. I'm a new anti-vaxxer."
Yeah, the labels don't help, I don't think, but it does strike me as that. I don't know if anyone here or watching is familiar with the meme where it's a dam, right? It's a dam with a reservoir behind it, and it says, "I'm not racist," and then there's a hole in the dam with water rushing through it, and over the water it says, "But," right? And I think we need to adapt that for anti-vaxxers. I'm not anti-vax, but there's
Yeah,
a
and
lot of that.
there's a meme that I'm gonna try and find. It's like when they say I'm not X, but you know this is coming. So
Yeah.
I'm gonna see if I can find that.
Yeah. Right.
So the first misconception that I have on my list here is that mRNA vaccines are new and untested, and this is super easy to refute because mRNA vaccines as a platform for just getting mRNA into cells and then expressing that mRNA, that's been worked on in humans for about 10 years. So it's something we've been doing. It's something we know how to do. It's not like unheard of. It's not something we came up with in 2019 and then all of a sudden we're like, oh, we can use this to make a new vaccine in 2020. It doesn't work that way. This is something that has been in development for a decade. Like that's just history. There's no counter argument to that. It's just this is something that's been worked on. It's not a brand new thing.
Yep. And people are so afraid of mRNA in the vaccines, but in reality, we eat far more mRNA on a daily basis than we get from a single vaccination. From what I
Yeah.
understand, and Dr. Jenny, you can correct me if I'm wrong, the actual mRNA from the vaccine, I think, when I read, it only stays in the body for like 5 minutes or something like that. If I
That was another one. So that was another one on here that, oh, the mRNA, it's a permanent thing in some way, right? So the mRNA itself, like not just this mRNA, but all mRNA is super unstable and it doesn't last very long. So this mRNA in your cells lasts minutes. I mean, you're talking on the outside, if you go super, super outlier cases, hours, a few hours, not like 24 hours, but like a couple of hours. But like you're talking, that's almost unheard of though. If you're talking 5 minutes, this stuff is gone.
yeah,
Right.
and
Like,
right, and people who say that probably don't even know what mRNA even stands for, let alone what it does.
yeah.
Um,
Just in
so,
terms of the concerns though of introducing this thing that's like going to permanently, like one of the myths is that it'll permanently alter DNA. Well, one, there's no opportunity to do that. It's gone in 5 minutes. Two, we don't have enzymes that like do that for real. I mean, telomerase is kind of a reverse transcriptase, but it has its own template with it. It doesn't just grab RNA. And then we have it's very rare for mRNA that our cells make to then kind of go backwards through the process. Like I don't want to put a frequency on it. 1 in a million, 1 in 10 million, like I don't want to put a frequency on it because I don't know, but it's an enormously rare thing to happen. And then let's say it did happen. Let's say somehow the mRNA from the vaccine in the 5 minutes it's present in your cells, and literally 5 minutes before it degrades. But let's say in those 5 minutes, somehow it gets imported into the nucleus of your cells, which shouldn't be possible, and it gets incorporated into the DNA of that cell where that happened, which again, we don't have like enzymes that do that as the thing they do. So like shouldn't happen. But let's just say, if all that happened, then you have changed the DNA for the one cell where that happened in your body out of trillions. So
right.
what?
Yeah, and just out of curiosity, Dr. Dan, when you eat, say, a banana or a piece of steak, how long does the mRNA from that food stay in your body? Just out of curiosity.
So mRNA is really unstable. You don't encounter enzymes that break it down until it gets to the small intestine, which is hours after you eat it. But mRNA just chemically is really unstable, so I wouldn't expect it to last more than a few minutes, but probably longer than in your cells, because in your cells you actually have enzymes that target mRNA and break it down, whereas in your digestive system you don't until you get into the small intestine. So it's going to break down just whatever its biochemical half-life is along the way. Your stomach is a really inhospitable environment, pH 2 hydrochloric acid, right? That'll break stuff down. But like it's gonna the mRNA you ingest is gonna last longer, I would think, than the mRNA in the vaccine.
Right. That's one down. It's been there's a development.
And
I think we covered. I think we caught two there. I think we're.
So another one I wanted to add to my list is the quote unquote dangerous ingredients in vaccinations, such as aluminum and some stuff that they are afraid of. Once again, aluminum. You have more aluminum from eating a banana than you get from a vaccination. And what exactly is aluminum used for in vaccinations?
Aluminum, I don't actually know. I'm not actually sure what the aluminum ingredient is. I know the one that everyone was afraid of for a really long time was ethyl mercury. But that's silly because our bodies don't incorporate or metabolize ethyl mercury in any way. It just goes right through us. The kind of mercury you have to watch out for, the kind that is subject to bioaccumulation, is methyl mercury. That's like what like when you eat tuna, like you can't eat too much tuna because mercury poisoning if you eat like a lot of tuna. And so it's just two different things. Now, even aside that it's two completely different things, our body treats them completely differently. Way back in like the early 2000s, I think we got rid of all the ethyl mercury out of vaccines for no reason other than people were worried about it. So like that's not even a thing anymore.
Yeah. So there's
It's a preservative. It's an antifungal preservative is why it was in there. It was part of a preservative. But we got rid of it, which actually makes vaccination harder because now you have to have vials that are smaller doses, like smaller numbers of doses, because you can't preserve them for as long because you're lacking this preservative.
Right. Immutable Destiny asked, is it possible for genes that are embedded on the mRNA to integrate into our own genome? And I'm pretty sure the answer to that is no.
Yeah, it's basically no. We don't have like enzymes whose job it is to incorporate mRNA into our own DNA. It does happen spontaneously, very, very, very super rarely. Like I don't even want to put a number on it. It's extremely rare. In order for this vaccine to do that, like I said, it would have to, within the 5 minutes the mRNA exists, it would have to not get grabbed by a ribosome in the cytoplasm of your cell. It would have to not get broken down by any enzymes. It would have to be imported into the nucleus, which it is specifically designed to not do. It can't do that. You don't re-import mRNA into the nucleus, and it would have to incorporate into DNA once it got in the nucleus. So no, it's not going to incorporate into your DNA. It's not going to happen. The next,
I say the other one I thought of medical is again is like I mean you might have to listen to it. I forgot, but it's like the government mandated this, rushed it.
So that's actually perfect because the next one on my list is these specific vaccines are not well tested, sufficiently tested. It's rushed. We don't know, blah, 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 blah. Well, so here's the thing. The clinical trials for these started way back in the spring of 2020. And they were initially small numbers. And then the phase 3 clinical trials started in the summer of 2020. And if you combine Moderna, Pfizer, and J&J, you're approaching 100,000. I don't know if it's more or less than 100,000 participants in the phase 3 trials. I forget which ones are which, but one of them had like 20-something thousand participants. One of them had like 40-something thousand. And I don't know what the third one had, but it's in the tens of thousands, right? So you're approaching 100,000 here. So that's 100,000 people that half of them were vaccinated. Actually, one of the trials, I think, was 2/3 vaccine, 1/3 placebo. But so roughly half of the participants, though, were vaccinated between I think it started in July or August and then up through like into the early winter of last year. So you already have now a bunch of people that are a year out from their vaccination, their original 2 shots or 1 for J&J. And then since then, so that's hundreds, tens of thousands of people, right? And then since then, just in the United States, we've got about half the country is fully vaccinated now. More than that, I think we're into the mid 50s, maybe approaching 60% now. I haven't looked at the numbers specifically in a couple of days, so I don't know what the specific number is, but it's above 50%. So that's now 160 million, 100, somewhere in that range, people that are fully vaccinated over the, starting in January, right? So now we're 8 months out for a lot of these people. That's a lot of testing. That many, over 100 million people. If there is something severe, something wrong, some side effect, we're gonna find it in in those 100-something million people, right? And that's just in the United States. That's not including everywhere else in the world where these vaccines are approved and in use, right? So it's just not, it doesn't pass the smell test to say that these vaccines have not been rigorously tested. And the icing on the cake for that is, we're recording this. It's Saturday, August 21st. The word on the street is on Monday, August 23rd, the FDA is going to give full non-emergency approval to the Pfizer vaccine. So like, that's it. That's the ball game. It goes through the same process as everything else. That's it. They've been vetted, they've been tested. Like, if there were severe something, we would know it by now. It's just not there. It's fine. It's been tested.
Yeah, I just hate that some of the, I don't know, the real medical workers or not, but a lot of people in the medical community aren't getting vaccinated apparently, because like my mom's nursing home got shut down a few times because some health workers there got COVID, but they're not getting vaccinated.
Yeah, and I just wanted to chime in. If you're anti-vax, you do not belong in the healthcare industry. You are a risk to your patients, and you're a risk to your patient's family. Anti-vaxxers do not belong in healthcare, period. And they don't belong in education either. So
I don't think anti-vaxxers belong anywhere. Every company has the power to say, like, you can be vaccinated or you can find a different job. That's perfectly fine.
Yeah, luckily my mom got vaccinated way before me. So.
Yep. And when I went to UMBC, they required pretty much my childhood immunizations and COVID-19. So mandatory vaccines have always been a thing. So next, one of the things next on my list is that COVID-19 has a 99% survival rate. Thus, the vaccine in fear is not needed, and you shouldn't live in fear of something with such a high survival rate.
That's a lot of death.
Yeah, but that's like 1%. That's like out of 7 billion people. That's like what 700 million.
It would be 700 million would be 1/10, so it would be 7 mil. It would be 70 million. 70 million people.
That's bigger than New York. That's bigger than New York.
Yeah, that is unreal. That's
pretty bad.
That's a lot. I mean, look, there's most diseases don't have a high mortality. If a disease has a mortality rate of 0.1%, that is a public health emergency, right? So if you have something that is 1%, that is a 5-alarm fire. We need to deal with this right now.
Right. And you also have to understand that polio and other very scary vaccines, childhood diseases that we eliminated thanks to vaccines, also had a 99% survival rate.
Yeah.
So,
but
there's a reason.
But it's not. Sorry. But both with COVID and polio, it's not just the death. It's survival. Even if you do survive both things, your body is changed. Either your lungs, like for COVID or maybe polio too, but your legs for polio. So
right,
polio
causes your paralysis for the rest of your life. Right. For COVID, it infects a whole bunch of different tissues and organs in the body in severe cases, or even not that severe cases. But when you recover, there are these lingering effects. I mean, there have been documented cognitive effects in months after recovery where people are testing negative. There have been lots of organ damage where people are requiring not just lung transplants but kidney transplants, and other organs are getting damaged severely. It's not either you die or you're fine. There's a whole lot of, real estate in between those two options where you survive, but you're not 100% recovered. And going back to the worry that people have, that some people express, I'll say, about long-term effects of vaccination, we went through why that's not serious and not reasonable. But the other side of that is, what if those worries are warranted? What if, let's just say, worst case scenario, whatever bad thing they say the vaccine might do, it might actually do. Well, let's just say, for the sake of argument, is that worse than the percentage of incidence of what some people are calling long COVID and the severity of those effects? No, the risk is still in favor, right? If you do the math, the risk reward is still in favor of vaccination, even if you assume that worst case scenario that is completely like unreasonable, right? But even assuming the unreasonable thing, it's still the better decision based on what we know for sure about the frequency and the effects of, long COVID, right?
Right. And the 99% survival rate, that might be true in certain groups, but in the very, very old or the very, very young, the 99% survival rate might be going to like 95%.
Fortunately, very young, is even higher than that, actually. For whatever reason, kids, for so far, don't get as sick as adults.
That's good.
So,
Yeah, but
So,
like we,
yeah.
And back
but-
to the 99. Sorry, back to the 99% survival rates. If we have a disease, if we have a virus like Ebola, Ebola kills pretty much 80 to 90% of its
Some of them.
patients. Yeah,
some of them are in the 20 to 30 range, which is still terrifyingly high,
Yeah,
but it's only a couple of outbreaks that have been like above
Right.
70%.
Right, and
Yeah.
20 to 30%. But you also have to remember, because they are so deadly, they're not going to be as contagious because of the selective pressure. And if you virus and you kill your host too quickly, well, you're not going to be able to reproduce and pass on to that many people. In contrast, the H1N1 flu from 2009, it was even more contagious than COVID-19, but in the US, only less than 15,000 people died.
Which is low for a flu season.
Yeah,
Like,
and
that's like half to a third of a normal flu season.
right. So we have the H1N1 was nowhere near as deadly as COVID-19, and the reason why is H1N1 was really, really, really good at passing itself along, making sure that its hosts weren't sick, too sick that they die, but sick enough to pass on, and that's it. So COVID-19 is probably one of the worst pandemics we've had in
100 years.
3 years.
Yeah,
100, it's been 103 years since the 102, I guess, since the pandemic started, since the 1918 Spanish flu, which isn't from Spain, but Spain
Actually,
let the news out.
from what I understand, actually, fun fact, because this was during World War One, the Spanish flu actually originated somewhere in Oklahoma, I think, but because Spain wasn't part of the war, they were the ones being honest about the death rate, and so all the other countries like the U.S., Germany,
Suppressing
they were deliberately downplaying it in order to keep the morale of the army up.
and
So-
not let your enemies know that everyone's getting sick and dying, right? Because I mean, World War I was the epitome of like right to like through 1917, basically anyone could have won. This is getting way off topic. Basically anyone could have won World War I, right? I mean, as of 1916, like Russia could have broken Germany's back with the Brusilov offensive, right? And it was like this close if they had like better leadership. And so in 1918 comes around and there's this terrible flu ravaging the entire world. All the people participating in World War I, all the countries are suppressing the news so that the other participants don't realize what a big problem it's causing. Spain wasn't a participant, and famously, I think the king at the time got really sick. And so, like, the news came out of Spain was being open about it, so it became the Spanish flu, even though it didn't come from Spain.
I'm going to say it came from Oklahoma.
yeah.
I couldn't tell you.
I heard that too. You should watch. You should watch the. You ever watch?
Actually,
You ever watch?
I was wrong. It's Kansas.
But you ever watch? David, you ever watch the extra credit series about history?
No, I don't.
They did a whole series on the Spanish flu, the history of it, where it came from. But before we go on, I just want to say, I think I mentioned this on last thing about vaccines we did, but I think it's ironic that some of the anti-vaxxers, at least, they're like, they say, "Oh, my body can handle it. I'll survive." but you know what that's called when you let your body and other things handle it. You don't do it artificially. It's natural selection. The thing most of anti-vaxxers
Right,
don't even believe in.
We're going to find out whose bodies can handle it or not, right? That's the trick.
Yeah,
So
most of the things that they don't even believe in natural selection.
So there's kind of a couple related things I want to touch on that tie some of this stuff together. So one, with the 99% survival rate, there's something else that we have to consider with this. And for other things, and like you brought up polio, for example, or, measles, mumps, like anything, from the, that we vaccinated against, during the 20th century, we developed a vaccine, we got rid of it, or mostly got rid of it because still measles outbreaks in this country. But what the thing with the 99%, it kind of ignores, there's two things to it. One is that for all the, polio, most people survived, or measles, whatever. The thing with that is because it was not new, it was something endemic to humans forever, basically, for as long as we've had human society. There were only so many people at a time that are susceptible to it, because by the time you got to adulthood, you already had it, right? So you weren't susceptible to it anymore. So you had, as kids, you had cohorts that were susceptible to it. But if 99% of the population survived it, it wasn't, you're going to kill 1% of the population in a single year or two, right? It was because there was only a tiny fraction that was susceptible at that time. And then just one other thing, what David mentioned about the different levels of vulnerability among different age groups and other things, with this 99% survival rate, and as an anti-vax talking point basically implies is, who cares if grandma dies, right? Because that 1% is not evenly distributed throughout the population. It's biased towards people who are over 60 or 65 years old. So what you're saying is, well, for me, the lowest rate of vaccinations among people who are eligible, it's 18 to 25, 25, I forget what the cutoff is, but it's like 18 to 25 year olds. So if this is like some 22-year-old idiot saying, well, my chance of dying is 0.000 whatever percent, right? It's like, yeah, but like grandma's is 10%. So like, what are you doing? You're saying that's okay?
Yeah, your survival rate might get, but you can still hold the virus in you, and you can still give it to her.
Yeah.
Right, exactly.
The other thing that kind of is related to this series of talking points, going back to the untested and, well, it's it's mostly survivable anyway, and yada yada yada. Now we're seeing a whole bunch of people that are using like untested treatments, right? I mean, this has been a thing forever with hydroxychloroquine, right? But now you see people using ivermectin, which is an anti-parasitic drugs for like livestock. Like, this is something that you give to horses and sheep, and there are like agriculture supply companies that are like, stop buying this from us. It's for horses. You can't use it to treat COVID.
Right.
You've got people that like state level health officials being like, stop doing this. There was one state, I forget which state it was, but over the last week, 70% of the calls into poison control for that state were for ivermectin, because this is there's no dosing regulations. There's no like, what does the course of treatment look like? There's no safety data. There's no efficacy data. There's nothing. I mean, these are people's, it's emergency usage, not full FDA approval, so I don't trust it. So I'm going to take this drug that's made for animals, for livestock, that is completely untested in humans instead. It's completely contradictory, and it makes no sense.
Oh, and I also want to point out that it is an anti-parasite drug, and by definition, anti-parasite and antibiotics do not work on vaccines.
On viruses, it's not antiviral.
Yeah, it's not antiviral, exactly. And antibacteria doesn't work on viruses because viruses aren't bacteria. And for the general scientific consensus overall, viruses aren't even alive. But I know there's some disagreement about that. But
I just found it. It was Mississippi's state, Surgeon General, whatever the state level thing is for Mississippi. This guy had to go out and like at a press conference say, stop taking ivermectin. It's for treating worms in livestock. It's not antiviral. It's not approved for this. It's not tested for this. Like, don't do it. This is dumb. This is ridiculous. Okay. So that covered like a whole bunch of things. Kind of the next set that I have here is the whole like breakthrough cases, right? Is it doesn't prevent COVID, it doesn't prevent severe illness, it doesn't prevent death, it doesn't prevent transmission. And then kind of related to that is that natural immunity is just as good. We have numbers on all of these things. So like, I'm just gonna there's a really good piece on Vox. This is from August 3rd. This is on Vox.com, and I'm gonna put this in the private chat here, and then I don't know if I can share links in the side chat, but
I think you can.
yeah. Oh, here, then I'll just share it directly. Here you go. There you go. This is a good piece. So this just goes through looking state by state, and there's a table. There's a big chart here looking at the share of cases state by state that are among fully vaccinated people, and you could just go down 4%. I think the highest was 5.9. Yeah, the highest was Arizona, which is 5.9%. Most of them are below 2%. So I mean, I'm not going to read all of them, but 4, 5.9, 3.6, 1.4, 0.2, 1, 1.3, 1.2, 1.1, 1.3, 1, 1.6, 3.2, 0.4, 0.2, 1.2, 0.8. Like it prevents infection. The vaccines prevent infection even against the Delta variant. Like this is not hard to see. The data are crystal clear. And I'll also note that if you have a state, right, that's like say state is 70% vaccinated, right? If the vaccines did nothing, zero effect, what fraction of cases would be among the vaccinated people? Should be 70% if the vaccines did absolutely nothing and a state was 70% vaccinated. So say that state is 7% of cases, right, are among vaccinated people. No states are that high, but that would indicate that the vaccines are 90% efficacy at preventing infection, right? Because the baseline would be 70% in this population. If the actual hypothetically was 7%, right, that's a 90% reduction, right, in your infection rate in that group. Every state is better than that. So, I mean, even with the Delta variant circulating, the vaccines are still preventing infections to the tune of 90%, right? Or like better than 90%, according to the data that I just read out.
I don't know if this is true or not, but I heard the Delta variant was created because some people didn't want to do social distancing and stuff. They got together in a big group, and that happened.
So I actually just did. I'm gonna do a little shameless self-promotion here. I just did a long thing. It was like 40 minutes long on the evolutionary basis for the Delta variant. It's on my channel, Creation Myths, and it's called Evolution Explains the Delta Variant, and it's all about the evolutionary history here. I won't go into all the details here because that would take another half hour. But
it's one of the, and I would say I'm a bit biased here, but I think that's one of your best videos.
Thank you, I appreciate that.
And I will say that this is why teaching and understanding evolution is so important, because evolution has a very wide applicability throughout all fields of science. You can't really pretty much understand anything in biology without understanding the basics of evolution.
Yeah. And I'll give just to make sure I cover not just infection, but also hospitalization and death. I'll give you some data from New Jersey specifically. These data are now a little bit old. These are from June 28th, but here's the data from New Jersey, right? The fraction of cases among the fully vaccinated, again, this is as of June 28th, was 0.08%, right? 0.08%. Now, the Vox piece was a little bit newer. It's actually gone down. In New Jersey, it's gone down to it's gone up to 0.2%. All the way up to 0.2%. So it's higher than it was in June in terms of fully vaccinated, which actually makes sense because we've gotten more people vaccinated. So part of that's going to be that as more people get vaccinated, the fraction of cases among vaccinated will go up. But so again, as of the end of June, it was 0.08% of cases were among the fully vaccinated, 0.002% of hospitalizations, and 0.0007% of deaths. and that is with a vaccination rate of a hair. As of the end of June in New Jersey, it was right at the cusp of 50%. Now we're up in New Jersey. Now we're up to like 70%. So like, yeah, go New Jersey. But yeah, those data are just, they're self-explanatory, right? Like the vaccine prevents infection, severe illness, and death. Full stop.
Yep. Okay.
So did you mention, was that a conversation that the vaccine is just that if you got it, you don't need the vaccine? Is that's something you mentioned?
Natural immunity. Yeah, let's talk about natural immunity. So we actually have data on this, and I have the link open right here. I will try to find it. Let's see. Here we go. This is from, where is it? Where is it? Oh, I thought it was this one. Where is the, oh, I had the wrong page open. It was somewhere on Johns Hopkins. It was Johns Hopkins natural immunity. Here we go. I'll find this real fast. Sorry. Here we go. So it's a piece called Why. Oh, is that link broken? Oh no. I think the link might be broken actually, because now I can't find it. Hang on. But it's called Why COVID-19 Vaccines Provide Better Immunity Than Infection or something. Find this real fast here. Why COVID-19 vaccines
While
provide
you're
better.
doing that, I'll just make this comment here.
Okay.
Is that okay? We have natural immunity. That means you have to get the virus, which means you have to risk dying from the virus, which means you also have to risk all the other complications that come with getting the virus, including long-term effects from the actual virus. So you're putting yourself at harm's way just for natural immunity.
So I'm going to put the link to this piece in the chat of the video here, because this is really good. It's an interview with a doctor going through, recovery from infection and then what protection that gives you versus vaccination. The big thing is that a vaccination, right, 2 shots, we're talking Pfizer is the one that's going to get approved on Monday. So we're really, and that's, I think, the most common one in the US. So that's really what we're talking about here. So it's 2 shots, but Moderna works the same way, where first shot gets you your primary immune response. Now that the antibodies from that wane, usually relatively quickly after 1 shot, or an infection, right? A primary immune response, usually the antibodies, weeks to months, right? A couple of months, maybe. But you make memory cells, so you see that virus again, and you could ramp up a response really fast. Instead of taking 2 weeks to really ramp up a response, it'll take a few days to really ramp up a response.
Yeah, I remember when I got my second shot, I felt out of it for a few days.
You feel it, right? That's your immune system doing what it's supposed to be doing. That's a good thing, right? That feeling a little bit achy, a little bit sore, a little bit tired, maybe even have a fever, like that's your immune system doing exactly what it's supposed to do. The nice thing is that second exposure, right, that second shot of the vaccine, once that triggers what's called the secondary immune response. It's faster, it's stronger, and importantly, it is more persistent than the primary response. So the antibodies that you make that second hit, they stick around. And like what we're trying to figure out right now with the booster trials is how long do they stick around? Is it 6 months? Is it 8 months? Is it 10? Is it 12? And what we're seeing is 6 months, you're good. 8 months, most people seems to be still pretty good. The question is probably like 10 to 12 months. In a lot of people, it's possible the antibody levels are going to drop off to the point where infection becomes more of a possibility again. So that's the idea now. I think they announced that starting in September, they're going to start offering boosters for the specific reason that once that antibody level starts dropping, you hit it with another exposure, bring it back up, and that offers, like the phrase is protective immunity. It's not responsive, it's protective, right? It's proactive. And acquired immunity from an infection doesn't do that because that's a single exposure, right? That's a single primary immune response, but you're not getting that second step that confers the long-term protection.
You have to go get it again. Go get sick again.
Don't do that. Don't go get sick again. Don't do that. If you already had COVID, go get vaccinated anyway. Go get vaccinated anyway. All right. Let's see. Oh, and the one other thing, kind of along these lines, is transmission. There's the thing going around that, especially with Delta being more transmissible, that vaccination doesn't protect against transmission. That's not true. It reduces transmission rates. The CDC really effed this one up, frankly, because they based their kind of press release on this, their findings on this, on that one study out of Provincetown. I don't know if anyone's familiar with this case, but there was a big cluster in and around Provincetown, Massachusetts, earlier in the summer. And based on those data, which highly vaccinated population, fairly large outbreak, but a couple important things to note. One, they probably overestimated the transmission rate. People have gone back and looked at those initial numbers, and they originally said it was like maybe as high as 8 or 9. It was probably closer to 6 or 7. 7-ish, I think, is kind of where it's settling now. So that's a pretty serious difference in terms of transmission rate. The second thing is that if that whole population was unvaccinated, given the number of cases that were caught, it actually should have been a bigger outbreak than it was, right? Indicating that there was, like, you could do the math based on what we know about Delta just kind of among unvaccinated populations. You could do the math with other strains of COVID. And given what we know from, at that point, a year and a half of experience, right? That actually, it's likely that would have been bigger, right? It's basically a certainty that would have been bigger had the vaccines not been reducing transmission rates. And also, last thing I'll say on this is that if you're preventing infection, you are necessarily preventing transmission, because somebody who doesn't get infected cannot transmit the virus, right? So to say that the vaccines are unable to reduce or prevent transmission is just, there's no basis for that statement. Like, the vaccines reduce transmission, period.
Yep. The next one on my list, and the last one on my list is vaccine shedding. That you risk getting other people sick with COVID because you're vaccinated and you're spreading the virus around.
All right, so let's tackle this. I'm going to write out a list of what's wrong with this. So first thing, the spike proteins are only made for the 5 minutes the mRNA exists. So remember, what it does is you put the mRNA in your cells, and then your cells make the spike proteins, right? So the first thing is that you only make the spike proteins for those 5 minutes, and then however many you make. And then those spike proteins don't last forever. Those spike proteins are gone after hours, days, right? They don't last forever. They break down. And they're also going to be bound to antibodies and ingested by cells of your immune system, right? They're not just kicking around until they break down, like they degrade spontaneously, like your body grabs onto them, right? So that's the first thing. The spike proteins don't last long. The second thing is the spike proteins are not infective. So, like, there are vaccines that cause you to shed virus, most notably the oral polio vaccine, because polio is it's an enterovirus. It's a virus that infects the lining of your digestive system, and it has to mutate to infect your nervous system, right? And so what happens with polio is the vaccine that was in use for decades was an attenuated vaccine, that it would be the live virus, but it would be a mutated strain that was adapted for a different host, so it didn't make humans sick, but it could still infect our cells. So, like, we poop it out into the environment, and then other people, in theory, could be exposed to that virus.
Kind of like
right?
what was it?
Cholera?
Yeah.
Cholera, yeah, it's the same transmission route as cholera. Yeah, exactly. So it gets into the water, someone ingests it. Yeah, exactly the same idea. Now, just as of like a few years ago, the whole world switched to an inactivated polio vaccine. So it's dead virus rather than live virus. Shedding isn't an issue there, right? Same thing. Now, this is even a different type of virus once the mRNA is gone. It's called a different type of vaccine. I said virus, vaccine. Once the RNA is gone, it's called a subunit vaccine, where instead of being the whole virus, but it's dead, It's just a little piece that your immune system grabs onto. Those spike proteins are not infective, right? They don't cause COVID. They're just the things that your immune system sees when it's responding to the presence of that virus in your system. So the presence of those specific proteins is sufficient to induce an immune response. But like, there's nothing, like you don't, it's just no. There's no basis for that claim. You don't shed SARS coronavirus 2 when you're vaccinated. That's silly. Yeah. So that's shedding.
Yep.
Let's see. So the next two that I have, this actually came from our Facebook conversation over the last week. So the next two that I have are connected, is that the vaccine causes infertility or miscarriage, and neither of those things are true. So let's talk about why. The infertility claim has to do with these important proteins that are necessary for building a placenta, right? Early in embryonic development in humans. These are the syncytins or syncytins. I've heard it pronounced both ways. And these are proteins that we actually acquired. We stole the genes from retroviruses, and now we use them. And they're actually they kind of suppress an immune response in utero. They prevent an inflammatory response, which allows the embryo to attach more robustly and facilitates the construction of a placenta. So they're really important. You need those in order to have placental development. So the claim was that the vaccine target, the spike protein, is similar enough to this protein in the placenta that it causes the antibodies to attack placentas, and therefore women who are vaccinated would then be sterile because they couldn't develop placentas. That's ridiculous. That's not the case. The proteins are quite different from each other. The antibodies don't target the human protein, the syncytins. They don't do it. It's just not true. And it doesn't cause infertility. If it did, we would be seeing a major drop off in pregnancy rates and birth rates right now and very soon, right? Because we're now, so long into this thing that it would be obvious if this was a problem, and it's not. Related to that is the claim that the vaccine causes miscarriages. There was I'm just going to pull up the CDC thing because this was a study. This was released Wednesday, August 11th, finding that the rate of miscarriage within the first 20 weeks of pregnancy. Now, I'll say the vast majority of miscarriages occur within the first trimester. And so the rate of miscarriages with the vaccinated population, this was a study of 2,500 pregnant women. The rate of miscarriage was 13%. The background rate in the first 20 weeks among the general population is between 11 and 16%. There's no difference, right? It's the same. And then just also, let's just see if this claim passes the sniff test. But because the claim that I was introduced to that I had never heard before was that actually it's double that. It's about 25%. Now think about that. Think about if this causes miscarriage to the tune of 25%, right? So now think about this. About half the population is vaccinated, right? So let's just assume that means half of all women are vaccinated. It's actually more than that because men are less likely to be vaccinated than women, but let's just assume, right? So now if we were seeing an increase, a doubling of the miscarriage rate among vaccinated women, and half of women were vaccinated, that is a net increase in the miscarriage rate by 25%. We would see that. That would be a nationwide, unhideable story, right? You couldn't hide that enormous an increase in the miscarriage rate. Right. The reason we're not seeing that story is because the vaccines don't cause miscarriages.
Yeah.
Right. And also, if I could chime in real quick, even if that argument were true, all what that would show is that women who are pregnant shouldn't be vaccinated. That's all what it would show.
Yeah.
And does not at all show that the vaccine should not be taken by those who are not pregnant.
Yeah, and why does the question that I would have is why does the vaccine cause it, but not the virus itself? If it's like a dead virus, it's like say you said it was immune virus or
Just a-
dead virus, whatever. What does the
it's
virus
just
itself cost?
you make a little piece of the virus, right? If that did it, then why doesn't I guess the claim would be that it's like some other part of the vaccine is big and scary. But I will note that these mRNA vaccines actually have less stuff in them that people tend to be allergic to compared to other types of vaccines. So even if you're like, again, not a medical doctor, not dispensing medical advice, but like just statistically looking at complication rates, what you see is that like for people who cannot get a flu vaccine, like they're allergic, to something in the flu vaccine, in many cases you could still get the COVID vaccine because they're these molecular vaccines rather than subunit or inactivated vaccines, right? They're one of the different types. There's less stuff in them and it's super pure, so you're less likely to be allergic to something in it, right? So like even that variant of the argument doesn't make sense. Plus, there's one other side of this, that what we know is that pregnant women pass the antibodies to their embryos, the fetus, and then also pass the antibodies via breast milk. So like there's the other side of this that says no, and also given the fact that like pregnancy is a risk factor for more severe COVID than the background level, right? Like there's the other side of this is like, no, like again, risk reward, it sure looks like you should get vaccinated if you're pregnant. Not a medical doctor, not dispensing medical advice. That's what the statistics show. Right?
And that's why most people, except for this one, they get vaccinated when they're babies.
Well, right. You want to cover all those childhood things that most people get before they're 10, and then you don't, so you don't get measles when you're 3 or 4 or 6, right? You want to, the earlier you can get the protection, the better, generally.
But yeah, this is older rumor. Less of the vaccine, but more the disease itself was the flu. It's just the same as the flu, and the flu has a bigger survival, more death rates or something like that.
Say that again. The flu has.
That's what they're saying last year. Rumor. The flu has bigger death rates.
That it was worse than the flu. Yeah, that was BS. It was never worse than the flu.
And it's the same as the flu. It's just the flu, whatever.
It's just a cold. The thing is now, with vaccination, we're basically making it a bad cold. And I talked about this in that evolution explains the Delta variant. But like with vaccination, one of the things we're seeing with Delta is it hangs out in your nose rather than your lungs. And the reason for that is that with the protective antibodies, in your nose, you don't have as dense blood vessels. So you don't have as many antibodies because antibodies hang on your blood, right? So the virus can get a toehold in your nose. If it can get a toehold, it can do it in your nose and kind of your upper respiratory system. But anytime the viruses try to go down into your lungs are like, capillary central, right? So they immediately get mobbed by antibodies when they go down there. So you don't get like sick because it's not in your lungs. If you're vaccinated, even if you get it, what we're seeing is it tends to resemble a bad cold because we're able to keep it to our upper respiratory tracts, right? Our nose and our sinuses, not down into our lung, right? We can prevent it from working down into our lungs. And like, not to be pessimistic about the overall outcome of this thing, but like, if this ends up as an endemic virus and you have to, worst case, you have to get, your COVID, your variant optimized, whatever booster, right? Worst case scenario. I think what we're going to be able to do is get a general, like this antibody targets every known version of this effectively, and it's good.
Basically,
right?
one and done.
Right. I think that's where we're headed, probably, within the next years. Like, that's really where I think we're headed.
Yeah.
But even putting that aside, worst case, say you have like flu, every fall you get your COVID and flu shot, right? You get a combo, right? If that takes it from being something that is genuinely dangerous to something that is a bad cold, that's a win, right? That ends the pandemic as a life-altering event, right? Because we can live with a bad cold, right? We can't live with COVID 2020 into 2021. Like we can't, that's not a sustainable situation, but we can live with a new version of a bad cold, right?
Yeah.
That's a thing we can do. And that's, as I see it, that is the worst case outcome. So like, we're getting there, folks.
Yeah. And I gotta say, I think people still say this, that we're sheep for believing everything they say. It's not like I don't know about you guys personally. It's not like we enjoy wearing masks too, you know. It's not like we like, well, let's outright mask, let's wear them.
No, I'm frustrated with this whole thing because this wave that we're experiencing right now, this is the anti-vaxxer wave, right? If everyone, and this actually leads into kind of the last thing on my list. The phrase you hear is if everyone who can get vaccinated does get vaccinated, then that will effectively end the pandemic, right? And that's basically true. Whether it ends it by hitting herd immunity for a persistent amount of time and driving the virus to extinction, or just getting to the point where it's basically not a big deal. It's a bad cold, and adults and kids and everyone's vaccinated and they're protected. Like, if everyone that can get vaccinated does get vaccinated, like, that basically is the end, essentially, as a society altering event in our history, right? This wave right now, I showed you the data before of all those single digit and sub 1%, percentages of the vaccinated who are getting sick right now. Like, if all the people who could get vaccinated right now actually had already done so, this wave would not exist. There'd be this persistent, relatively low level of transmission and infection, but it wouldn't be what we're experiencing right now, especially across the south of the United States, where you've got hospitals full, no ICU beds, right? That would not be happening right now. This, to an extent, not true for all the prior spikes that we saw, the original one, the summer one of 2020, the winter 20 to 21 spike. Those, to some extent, were baked in, right? There's behavioral constraints there, right? But like, the virus was out there, people had to live their lives. You could do things on the margins to I shouldn't say on the margins. You could effectively bring those peaks down with distancing and masks and lockdowns and that kind of stuff. But like, again, that's not sustainable in the long term. But this spike right now, this is optional, right? So like, I've been responsible. My family's been responsible. I'm getting pretty fed up with this, right? I'm ready to go back to normal. I'm about to start my third full semester of teaching via Zoom, and I hate it. Right?
Oh, God.
And
I
you know
hate
why I can't go, and you know why I can't go back to teaching in person in a week? Because anti-vaxxers have caused coronavirus to still be a major problem, right?
Yep. And is Rutgers this semester all online still?
It is a mix. So for there's capacity limits in the classrooms. So basically everybody is in a room that's twice the size of what they normally would have been in, which for most classes is fine. If you had 30 people, you just go in a room that seats 80, right? No problem. For me, I got 499 people in a room that seats 499. It's the second biggest room on campus. My colleague who teaches the other two sections of the class I teach, she's in the biggest room on campus. She's got 500 people in a room that seats 500. There's nowhere else to go, right, for us. Yeah. So we're still, the big classes like that are still remote for one more semester.
Okay. I would honestly hate being in a class of 500 other people.
Oh, it's fun. It's we can talk about that another time sometime.
Oh yeah, that'll be a lot of fun. But not for now. Most of my, pretty much all of my classes are on campus. So
that's good.
That's good. And I would say I'm very glad, because I hate Zoom classes. I really hate online classes, and my grades kind of suffered when COVID hit.
Yeah, it's hard to focus, right?
Yeah, it's hard to focus, and I just miss being in person, being able to interact with my fellow students, and being able to interact in person with my teacher, because it is definitely different from being able to sit down in person and learning with them versus going on a StreamYard or Zoom and having a conversation.
It's richer when you can have a conversation, and just to illustrate and I kind of lost my train of thought, and I'll go back to my point in just a second, but to give you an idea, when I do like my classes, I do it asynchronously, so I record it, people watch it, and then we do kind of the office hours over Zoom, and when I record the lectures, it's like 45 to 50 minutes. But when I do them in class, it's an 80-minute period, and sometimes I won't finish because of the back and forth, right? And it's just such a richer experience. Even with that many people in the room, you could still have that conversation. So.
Right, because you have people stopping you every 5 minutes saying, "Hey, I have a question about this. Can you go back to this slide?"
Yeah. So the point that I meant to make, and then I totally just forgot as I was ranting about anti-vaxxers. I apologize, everybody. The point was that you hear this thing about if everyone who could get vaccinated does get vaccinated. And there's always this kind of caveat of like, well, there's a pretty significant slice of the population. I don't know what percent people think, but there's a bunch of people who can't get vaccinated, even once we, get to like where kids are eligible, right? And the thing that's important to note here is there's a big difference between the vaccine might not be as effective for you and you cannot get vaccinated, right? So there's people that are allergic to something in the vaccines. They'll have like a pretty severe reaction if they get vaccinated. That's very rare. That's well under 1% of the population, right? And then there's people who are immunocompromised, right? People who are organ recipients, who are on anti-rejection medication, right? Those are people where there's nothing preventing them from getting vaccinated. It's just that it might not work as well for them. So instead of being 90% or 95% risk reduction, maybe it's only 50% risk reduction for them. And for all those people, whether they just straight up can't get vaccinated or it's less effective for them, for all those people, it's on everyone else to protect them, right? But we always have this caveat of there's some fraction of people who can't get vaccinated. And I think kind of mentally people have that fraction as like 10 times bigger than it actually is, because the actually cannot get vaccinated is a much smaller fraction than the might not be as effective, right? And that's an important distinction to make when we talk about who can get vaccinated.
And that's the difference between people that choose not to get vaccinated, like the my body, my choice thing.
Right. And as the saying goes, your right to swing your fist stops at my face. Right. And this is not like a new idea. This is settled law, right? There was a Supreme Court case from 1905 about this. I think I have that right. It was 100 years ago, right? About this exact question. Can we mandate vaccination? Yes, we can. Yeah, this is not an open question.
Yeah. It also was the freedom of speech thing. It doesn't like for like saying fire in this theater or something like that, whatever that word was.
So that's actually a funny misconception that it's so that example is actually not like everyone remembers the saying in the decision, but the wraparound to that is it's actually not good law anymore. Like you can actually like do things like that. It's a little bit it's more complicated than that one.
Okay.
That one is made out. I really like this question here from Icarus that people want to wait for the dead virus stuff. Those are out there and in development. And oh my goodness, there was a podcast episode on this on the Chris Hayes podcast called "Why Is This Happening?" which is just the most perfect title for a podcast, in this day and age. And he did an interview. This is from last year at some point, but it was really good. If you go back through it, it was "Why Is This Happening?" It was about vaccination. And one thing the guest talked about was all these other vaccines that are in development, because mRNA vaccines are finicky, right? They need to be at low temperatures. RNA is unstable. There are a number of older style, either subunit or inactivated vaccines that are in various stages of testing right now. And some, I don't know what all the different vaccines that are approved are around the world. I don't know what all of them are. I would be surprised if there were not already some subunit or inactivated vaccines in the mix. So that's a really good question. And those vaccines are coming / already here. The thing to note, though, is that the mRNA vaccines, again, typically lower levels of complications in terms of like direct like allergic reactions and stuff, and generally more effective than those older types of vaccines.
Like the Johnson & Johnson vaccine, for example, that older type vaccine?
That is also a newer type. That is a vector. That is a viral vector vaccine. So that uses a different virus loaded. Instead of having its own DNA, it has DNA that codes for the spike protein. It gets into your cells, and then the cells make the RNA and then the spike protein. So it's similar to the mRNA vaccines with an extra step at the front end, right? So it's a very similar concept.
Is that why they only needed one at the time?
I don't know. I don't know enough about that to know why it's 1 versus 2 doses. I don't understand that one. Yeah, sorry.
All right. Anybody else have any questions in chat, or is that all your rumors that you broke down?
we hit just to some. So let me just look at my sheet here, because what we hit on, we hit the degree to which they are not new and have been robustly tested, the possibility and not possibility of long-term effects from the vaccine. We talked about how well they prevent COVID, how well they prevent severe illness, how well they prevent death, how well they prevent transmission, how natural immunity is not as good as vaccination, how they do not alter your DNA, how the 99% survival argument is just like callous and like not a good argument. Things like ivermectin or hydroxychloroquine are not viable alternatives to vaccination. They don't cause infertility. They do not cause miscarriage. There are some people who straight up can't get vaccinated, but it's a very small number. Most people, almost everybody can. And then for a larger, still small, but a larger fraction within that, it won't be as effective for one reason or another. And then we also covered shedding. There's no problems with shedding, period. Right? That's what we covered. I think that was pretty good.
Yeah, I think we have one last question. The AYV3.
No idea. No idea. Haven't even heard of it.
All right. Well, thank you for being on. Hopefully, both of your kids are still too young to get vaccinated, right?
They are too young. They are too young. But I will tell you, we will be first in line when they, as soon as we hear, we are getting them. We're getting them their vaccination.
Yeah.
So right again, I want to say, like, for people who are skeptical about this, don't ask what. Here's something I think is really useful. Don't ask people what they think you should do. Don't say, what do you think I should do? Say, what did you do and why? What is your family doing and why? What do you recommend for your grandmother? What do you recommend for your kids, right? Those are the questions to ask public health officials, politicians, people in the news, right? Because, like, you got Tucker Carlson up there every night spreading misinformation. That guy's vaccinated, right? Yes, him.
I'm sorry. I have to say how much I absolutely detest Tucker Carlson. He is a traitor and a menace to public health. I do not like Tucker Carlson. Oh God,
one of the single most destructive people on earth right now. Like, not an exaggeration. It's like Mark Zuckerberg. Like, there's probably some other people up there, and like Tucker Carlson, probably like top 20, maybe top 10. I don't know, somewhere in there.
He's honestly worse than Rush Limbaugh.
Well, yeah, because
Well, I was talking about, like, if Rush Limbaugh was still alive, he'd be worse than Rush, and he would probably. And I dare say he's even worse than Alex Jones.
Yeah, because I mean, Jones is so out there. He's got a small audience, relatively small audience, whereas Tucker just plays the right side of pretending to be reasonable so that he gets this huge audience, which is like.
And then of course, faux news argues in courts that he nobody reasonable would think he was speaking the truth.
We'll see what's going on with.
Yeah. Before we go, I think I mentioned this thing too. Is at least from growing up, to me, anti-vaxxers, again, like I mentioned before, that when I was growing up, anti-vaxxers, I always thought they were just far left people, like the altered medicine theory people, the crystal medicine, and I thought the right side people, were rare about. They were the rare branch, of it. The anti-medicine religious cult thing, people. But I'm hearing a lot more right-sided people.
It is,
nowadays.
And I think it's like everything is polarized by political identity, and I hate to be one of those like, it's such a shame that everything's polarized right now. But like, it makes it impossible to respond to a public health crisis when, like, if a bunch of Democrats say get vaccinated, the de facto Republican position becomes don't get vaccinated, right? That is a problem for society.
Oh yeah, and,
like, that's not sustainable.
Yeah, and I dare say if Donald Trump won re-election, we'd see a lot of people on the Democrat side being more hesitant because they don't trust Donald Trump. They don't trust Donald Trump's FDA.
I don't
And
think so. I
yeah,
think, I mean, man,
and,
I think
and
people would be jumping in on this. I mean, look, I got my second dose of the vaccine in the trial the day before election day. So,
Yeah.
you know, like,
Yeah.
it's
not.
I'm in, man.
Well, like I said, the real people aren't polarized. They're just doing it because they know it's right. They know science is right.
Yeah.
And it's not about who invented the vaccine, which party. It's just that there's disease out there, gotta get vaccinated.
Yeah, there used to be things that were beyond politics that everyone would do and everyone would get behind, and now it's not. And here we are. Yeah.
In today's world, if Democrats said wear a seatbelt and wash hands, the Republicans would be saying freedom.
Yeah, it's the same. Yeah. Don't get me started.
You think I can make your channel you want to advertise?
I just
so go ahead, David. Yeah.
Okay, sorry. I just had a really good conversation with Leo Felius on my channel on physics and how physics refutes young recreationism. You should totally check it out. Jordan was on for a little bit and he was talking a little bit about nuclear power, or not nuclear power, nuclear physics and radioelectric dating. So that's a great conversation. I had PZ Myers on my channel as well. That was a lot of fun. Oh, I know. It's great. Did you see my interview with
Myers for like dude, I've been so busy. I actually have the number of, so I actually earlier had to close about 20 YouTube tabs because my computer was yelling at me.
Yep. I don't blame
so, but I still have yours open. I still have two of you. Actually, I have your one from earlier tonight because it was going on while I was getting children to bed, which is when a lot of this stuff goes on. So I have both of those on deck, in addition to a bunch of other things.
Yeah, and what's coming up is Leo Felius and I are planning on doing a show looking at the Dr. William Lane Craig debate with Sean Carroll on God and Cosmology.
Oh, that'll be cool.
Dr. Dan, have you seen that debate?
Nope. I, as a rule, I cannot stand William Lane Craig debates because it gets all physics and philosophy, and I just don't have the stomach for either of them.
Yep. I enjoy the philosophy stuff. I'm a philosopher.
I can't do the philosophy.
I
can't do it.
But it was a really great debate, and you should at least listen to Dr. Sean Carroll's opening statements. Spoiler alerts: I think Dr. Sean Carroll destroyed William Lane Craig and ripped him up and shoot him out. But that's what you have that's what you generally get when you have a physicist, a cosmologist debating a philosopher on cosmology.
Yeah.
Right.
So Dan, you obviously you've been busy with your new family and class now, but you continue the series that you were doing on Wednesdays or Tuesdays, Wednesdays, what that series was about.
So the Evolution for Creationist series, is that the one, or just I mean I don't have a specific plan. So actually, I think this week, David, are we doing our thing on Wednesday? Is that happening this week?
This Wednesday, I think
are we doing our? We have something set up. Isn't it this Wednesday, or is it next week? I don't remember.
I believe it is this Wednesday. Yeah.
I think we have a thing for the. I think we're doing a thing this week, so that'll be cool.
Yeah. And Wednesday might. I'm starting my new job next week. Are you possibly available Saturday by any chance? If not,
at night maybe.
Okay, yeah.
Oh, but next I don't know. We'll talk. We'll figure it out. We'll find a time.
We'll keep it on Sunday.
And then let's see what else. I don't have anything specific, so I just put up a short video on creationists using the term Darwinism to describe all of evolutionary theory, which they know is wrong. They're just lying. They know it's wrong. So that was one I've been wanting to work on for a while. I do have. I think I've told a few people this, but this is, I think, the first time saying it publicly. I have a collaboration in the works right now with Aaron Ra on some genetic stuff. So I don't know when we're going to when it's going to see the light of day, but I'm hopeful that it's soon because he just did a debate with Dr. Charles Jackson and some genetic stuff came up and he kind of through the grapevine ended up finding me, and so we're collaborating on
Yeah.
that
Yeah.
stuff.
Yeah,
I don't know when that is, but at some point.
Yeah, two
Yeah,
things for I do my thing. Is one, I love it when they say Darwinism, like evolution genetics hasn't changed in 150, 200 years. Nothing has advanced at all. It's still Darwinism. And two, I love it when they say, I was in an Atheist Junior's video, this the evolutionists say this is why the Grand Canyon was formed. No, maybe geology says that. Nothing to do with fucking evolution.
Not the same thing. Yeah.
And also, well, for me, my next week, I have planned to have a video of Erica, aka Jessica Gibbon, about her namesake, the Gibbon primates. That's the plans, but sometimes plans, don't go out. That's my upcoming video for next Saturday, about 6 p.m. EDT.
Awesome.
All right, so David, you were saying before we go?
Oh yeah. That'll be pretty much it. So I'm working on a couple of videos, and that'll be a lot of fun. So definitely subscribe to my YouTube channel and hit that subscribe button. That way you can be notified when my next video and interview is up. And I have a very big guest coming up, and his name is Dr. Stephen Freeland. He is a professor at UMBC. I'm not sure if any of you guys know who he is, but he does. He is evolutionary biologist. He does work on abiogenesis and astrobiology, and and he's also an evangelical Christian. So we're going to be talking about how he was with BioLogos. Not sure if you guys are familiar with. And so we're going to be talking about abiogenesis, evolution, and God, and how all of that relates together. So it is going to be a great show.
That's going to be super cool.
Yeah, I love when people don't have to use their religion to deny science.
One of the things that I'm going to be trying to do is trying to get professors and scientists at UMBC to come on my podcast, because that'll be a lot of fun. I'm also trying to get. I'm going to have to talk to her, Dr. Myers. I think is. Oh God, I'm bad at names. Dr. Meyer. I think she's Dr. Meyer. She's an astrophysicist at UMBC, and I'm gonna hopefully try and get her on my channel. It's gonna be a lot of fun. So I have a lot of fun stuff in the works. So don't miss it.
All right, great. So you all want to say your Indian catchphrases if you have one?
I always end my creation myths videos where we go through a creationist claim. I always end with "Don't get fooled," because it is at the end of the day a PR campaign, not a science campaign, and don't get sucked in. So there's your COVID misinformation corrections. Don't get fooled.
Yep. And so I really don't have any catchphrase. I need to come up with a catchphrase. I think it'll be fun. But Dr. Dan will be on my channel next week. It's gonna be a lot of fun.
We'll talk. We'll figure it out. It'll be fun.
And as I always say, never stop learning and enjoy the randomness. I'll see you next week. Bye. Hey, thanks for watching my podcast or Let's Play. If you want to help support my channel, you can make a monthly or yearly pledge on Patreon, or just a one-time donation on Vimeo, PayPal, or Cash App. For those looking for something to wear, we have some shirts, hats, and other stylish things in our merch store. If you enjoy gaming, you can always follow and sub to me on Twitch. For those who don't want to give money, I have an Amazon and Steam wish list who can help the channel out. And of course, just liking, leaving a comment, and sharing this video helps more than you can imagine. And always remember to never stop learning and enjoy the randomness.